There you go. I like that. Well, I can talk a little bit better today, so that's a good sign. So I apologize to everybody in the audience if you couldn't hear me too well yesterday. That's why we have a loudspeaker, right? I'm a bit better. By the time I get home, I'll probably be back to normal, and my wife will keep saying, "Stop shouting." All right, we are going to continue what we did where we left off yesterday. You notice I've changed the schedule just a little bit. We only talked part of the time yesterday. My fault, I couldn't talk longer about EDS. We're going to continue on EDS, take a break, then do eels. Then after, I think realistically, after we finish eels, Hamish and I should get together, and if there's any questions from the audience, we should address it. But that's realistically a lot to cover. We've covered a lot of territory in the last few days. So I think we'll get together if anybody's got any burning questions, either on anything we talked about or on something that you're doing that might be related and you think we might be able to answer a question for the audience, everybody, we should do it then. And then we'll close for then. All right, I'm going to stop this guy and go back to yesterday. The last thing we talked about was different kinds of windows on the detectors. The fact that we could remove the window and do light amount analysis. And in a modern machine today, we can go anywhere from beryllium to uranium. Okay. All right. Now, intentionally, I'm not going to talk about the computer systems per se. It's a lot easier today than when Hamish and I first started this. When Hamish and I first started this, we had to put together our own electronics, data acquisition systems, pulse processors, everything to get all the... Nowadays, actually, this was by the time I left left Illinois and Oak Ridge and came to Argonne, we had continuous systems, self-contained. Nowadays, you can put it all in a single computer with a single board that replaced all this electronics. So life is a lot easier for all of you today. Okay. All right. And I'm not going to talk any details about that. That's electronics and processing. Can we talk about it if somebody's got a question? Yes. What I'd like to start talking about today is, I told you how the detectors were made. I told you how the detectors work. Now it's important to understand that they are detectors. There are artifacts in the detectors. I want to talk about those artifacts. So remember, I told you a signal comes in, hits our detector, creates electron hole pairs, and we amplify that and measure it. And that gives us our signal. Now, the important thing to remember about the detectors is they are not sensitive to X-rays. They're sensitive to energy. Okay? So, are there artifacts associated with energy being deposited in the detector that arise and get processed and then look like signal? The answer is yes. Okay, there's a whole slew of types of artifacts, and first thing, it's not an artifact per se, but it's fundamental of the operation, is the fact that the resolution of our spectra changes with energy. Okay, you can see that example right here. Here's a low energy peak, here's a high energy peak. The width of this is smaller than the width of that. Okay, the reason for that is that the energy distribution there is governed by an electronic noise plus a factor called the Fano factor plus a statistical distribution times the energy of the electron, the energy of the particle that created the signal. Okay, so basically, as a function of energies, low energy peaks are narrower than high energy peaks. Now, ideally, we'd love it if the low energy peaks had infinitely small width, and you'll see why later. But that doesn't happen because there's a factor called electronic noise. That electronic noise has to do with the preamplifiers and amplifiers of the detector. It's never zero. Okay. So in a modern system, that electronic noise really limits the lowest energy resolution we get. Typically, down in this low energy regime, energy resolutions from anywhere from 60 to 100 evolts are good. and that limitation is based on the noise. As we go up in energy, the noise doesn't change, but the energy changes, so the peaks get wider. Okay, you'll see that's important in a few minutes. The other important thing is we talked about a peak, an energy coming in, giving rise to a peak. Now, the crystal is sensitive to energy. If an X-ray comes in, it creates a number of electron hole pairs. If two X-rays come in at nearly the same time, they're just depositing energy in the crystal. Crystal doesn't know that. It says, I now have n electron hole pairs, and it'll give you a signal a little higher. Okay? Typically, that's called a sum peak. Two peaks come in at the same time. Okay? So you will see some peaks at the coincidence energy of two X-ray lines coming in. Normally, the sum peaks will be some peaks for the most intense lines. Why do I tell you that? I'll show you a few examples later, but whenever you go across, when we start talking about how to analyze these spectra, first thing you want to do is say, what are all these peaks? Is this nickel? Is this aluminum? Is this silicon? What is it? So you should first identify every peak. The way we identify peaks, remember we said, look at the energy of the line, look up a table of what X-ray line should be. Sometimes you're going to see peaks here going, it doesn't make any sense. Check to see if it is a sum peak. Typically, go to the highest intensity peak, double it. If you have a peak energy there, it's a sum peak. And we'll tell you how to identify that later. That's sum peaks. Escape peaks also happen. What's an escape peak? Let me actually go forward, because I think I've got very specific examples of it. Yeah, so let's go forward first for a minute. I went ahead of myself. Let's step back a second and talk about the resolution. Okay? I already told you there's noise and that the peaks get wider as we go up in energy. The other important thing to realize is the peaks have a width. And that width is governed by several factors. One, number of electron hole pairs that you get. I gave you an exact number. It's never exact. There's always a Gaussian type distribution. Okay? So that's going to give rise to a little bit of native width of that peak. So it won't be a single point, but it may have a little small distribution. The other thing that is important about the width of these peaks is the ability to measure the peak is proportional to how accurately we can count those number of electron hole pairs, or how accurately we can measure the voltage that's generated. Okay? And remember I told you when an X-ray comes in, we get a pulse, then a time delay, then another pulse for the next X-ray. The level at these tells us the energy of the X-ray. The longer the time we have to measure the width of that pulse and reduce the statistical noise, the more accurate the peak is. All right? And the more narrow the peak is. So all detectors have a parameter called the time constant. How long we're going to wait while we're doing a measurement to find our integral. Now, you say, well, we'll just put a really long time constant. That's good, except if your time constant is too long and you get two peaks coming in, two pulses coming in, you start getting overlap. Okay? So the time constant is a parameter that you can control. The longer the time constant, the narrower the peak. The shorter the time constant, the more statistical error you have in your measurement, the wider the peak. Why would I want a long time constant versus a short time constant? I want a long time constant to get good energy resolution. I want a short time constant when I have a lot of peaks coming in, and I want to separate them. So it's a fundamental limitation. You can either have a high count rate, lots of counts coming in, but you lose a little bit of resolution, or you could say, my count rate is very low, I can increase my time constant and get better energy resolution. And you'll see that has an advantage. All right. Why do I want that? Here's an example of, these are real measurements of X-ray lines. And remember, we can walk across the periodic table, going from boron all the way through silicon and keep going. This is some fairly old data from 1982. That's great. We can see all these elements. We can see carbon, oxygen, nitrogen. But remember, in a real world sample, we're not just looking at pure oxygen. We're looking at a compound that's composed of more than one element. Let's, assuming we're working with a transition metal. I already told you transition metals have very nice lines in the K series. Very nice, very discrete. Remember, you can't select which X-rays you measure. If an X-ray gets created and generated and hits the detector will measure it. So if we're interested, for example, in titanium, there's a few people who might want to look at titanium. We'll get the titanium K line. It's a nice line, we can look at it. But in addition to the titanium K, you will also see the titanium L, okay? So there's the titanium K in yellow and there's the titanium L in yellow, okay? That's not a problem unless you also want to look at another element that might be in this regime. For example, nitrogen. Titanium nitride is an important issue, okay? Look where the nitrogen K line comes out, and look where the titanium L shell family comes out. They superimpose directly. So because of they superimpose directly at the resolution we have here. If we had higher resolution, we'd be able to differentiate between those. And we can do that, and we'll talk about that, by either, sorry, I think it's the next slide. Yes, when we can't resolve it, maybe we go to a different spectroscopy. For example, electron energy loss spectroscopy, where we can now resolve the nitrogen from the titanium without too much difficulty. But then there are other issues. Okay, so resolution is a fundamental limitation. The other limitation is, I mentioned electronic noise, energy being deposited into the crystal, okay? Here's an example of the same sample in a noisy environment, okay? What's happening, we're actually vibrating the crystal a little bit. It's adding energy to the system. We're getting small bits of signal, and the noise is increasing. And we see, what does it do? It drowns out the signal at the low energy end. Why? Because the noise is high frequency. We have a long time constant. It washes this out. How can you get noise like this? Several ways. If you have an older detector with liquid nitrogen filling, if you filled up the liquid nitrogen too much and the nitrogen is boiling, it's creating vibrations, mechanical issues. I had a colleague whose name was Dean. You might know him, Dean Miller. Used to like to bring a radio into the microscope with him so he can listen to music while he was doing his microscopy. Of course, if you turn the music up too loud, not only did it vibrate the microscope, it vibrated the detector, and then you can get electronic noise. And there's other ways of creating electronic noise, ground loops and the like. So electronic noise it reduces your resolution. You can see the resolution gets worse and also creates additional peaks. I'm going to skip this slide. I mentioned that there are other artifacts in the detector. An X-ray can come in, create the number of electron hole pairs. As long as we measure every X-ray, when an X-ray comes in, it starts losing energy. Sorry, I should say it first. It starts losing energy. For example, let's say a 10 kV X-ray comes in. It takes 3.6 eV to create of that energy to create an electron hole pair. That's one electron hole pair. And that X-ray will continuously lose energy. Now, if that hits the crystal and the entire X-ray gets absorbed by the crystal, it'll create a single peak. However, what happens if the X-ray comes in, doesn't hit the center of the crystal, but really hits toward the edge? What can happen? Some of the X-ray energy, some of the X-rays can be missed, lost, okay? The amount of energy that's lost is called the escape peak. It's the amount of energy needed to ionize silicon. That is a very discrete energy. It's 1.74 keV. So if you take any peak, subtract 1.74 keV from it, you may see a nice small peak, okay? It will directly be proportional to the intensity of every peak, but it'll be very small, okay? So if you have a very small peak, you put your marker on it, you say, what is this peak, because it doesn't exist to an element that we know. Add 1.74 to it and see if it's next to if it's an escape peak from a large peak, okay? That will always happen. It may be very weak, it may be so small it'll be in the noise, which you'll only see it for very large peaks, because it's a specific percentage of the total intensity.
Can you say like
1.74 is the energy needed to ionize silicon. Your detectors are made out of silicon. Okay? So if the X-ray escapes before it finishes ionizing all the energy, it's because it's ionizing silicon, and silicon's releasing an electron hole pair. So it's always 1.74 keV. The other thing I mentioned is what happens when two X-rays come in at the same time. It's called the sum peak. So here, let's take a sample of iron, okay? And we're going to go in a very high count rate situation, lots of counts coming in. So we are getting individual X-rays coming in, but they're coming in so fast, and my time constant is such that I'm measuring it over a long enough interval. I'm seeing not a peak at 6.4, we see that one, but we also see some at 12.8, double that, okay? Now, how do we know that's a real peak versus a sum peak? It's very simple. These sum peaks are proportional to the count rate. So if we take the same area of the sample, decrease the count rate, what will happen is the peak will disappear. Okay? It's an easy way to differentiate between a sum peak and not. But notice the escape peak doesn't. Because the escape peak is a function of the primary peak. The sum peak is a function of the count rate. So always look for sum peaks and escape peaks in your spectra. They'll always be there if you have high enough count rates. All right. Those are the major artifacts in a detector. Energy resolution, energy distortion, sum peaks, escape peaks. I mentioned pulse pileup is similar to a sum peak. The peaks are coming down. Usually you don't have to worry about that now. The electronics nowadays are much better than they were 30 years ago or 50 years ago. All right, so you all are now experts at X-ray detectors, right? X-ray detector is useless unless you get it onto an instrument. So I want to spend a few minutes talking about the geometries that are possible. Basically, what we're going to try to do is we have a specimen, we have a beam coming down, we want to get our detector as close as possible to the specimen. So typically, what do? We have our beam, we have our sample, and everybody will draw you a picture that looks like this. We just put the detector in as close as possible. X-rays are generated from the sample, and they enter the detector. Well, that's true. The issue today is it's never just as simple as this. This is the actual picture of the inside of a microscope. I've taken it apart, but I've cleaned it up quite a bit because in this particular microscope, it's one of the ones that I take apart and put together all the time. So this is a real simple one. We have the upper and lower pole piece, we have the detector, and the sample comes in the middle. I've taken out all the other stuff. Real world doesn't exist like that. Also, in the real world, we have today a lot of different types of detectors. When we first started, we had simple round detectors. They were circular in diameter. They were about 3 millimeters in diameter, and roughly 3 millimeters in diameter, okay, and a certain thickness. Nowadays, we can buy round ones, rectangular ones, square ones. We can put one detector in, round or rectangular. We can put in multiple detectors, or we can put an array of detectors around the sample. All of that affects how well we collect X-rays. Why will that be important? If you want to measure something, you want to measure it quickly, you want to measure it accurately, and you want to count all of the signal. Okay. The other thing to realize is different microscopes have different geometries. These are pole pieces. So that's the kind of sketch you'll always see of a pole piece. These are real pole pieces. This is a pole piece from a 1,000,000-volt microscope. Okay. They all have a similar shape. That's more like the pole piece you'll have in your Titan. That's a 300 kV twin lens. But you have a gap, and between the gap, somehow, you have to put your sample stage. All right, as soon as I do that, what's happening? I'm starting to fill up the space. Somehow, around that sample, I have to get my X-ray detectors in, okay? And I want to get the detectors as close as possible. Of course, getting them as close as possible also depends upon the size of the detector, okay? The important parameter that measures how well a detector collects signal is something called the solid angle, the collection solid angle. And that collection solid angle is defined by the surface of the sphere that the detector intercepts over the radius squared. Okay? A lot of manufacturers just tell you the area of my detector divided by the square root of the radius is your solid angle. That's good if the detector is way back here. If the detector is very close, that equation is wrong. That's the correct one. Why do I tell you this? Because I want you to understand what kind of detector you have and how good its collection efficiency is. You can model this properly. There's a lot of equations, and you can look them up here on how to model the solid angle of your detector, knowing the full geometry, whether we have a single detector that's looking down at the sample, a single detector that's come in on the side because we're trying to do it simple, a rectangular detector, an array of detectors. That's all mathematically modelable. And you can write all the equations down, or you can log into this website and put the values in and give you an approximate number. Okay. Why do I say that? Because a lot of manufacturers will tell you a number which isn't real. They tell you the optimum number. This is what our solid angle is, and they frankly get it wrong almost all the time. Okay. How does the solid angle vary? Remember, I told you it varies upon 1 upon r squared. So this is a log scale and a log scale. When we first started doing work back in the 70s, I hate to say that, our solid angle was on the order of 0.01 steradians. That means we're detecting about 0.2% of all the signal that's being generated. We were happy with that. Hey, we got X-rays. As the years passed, we put in from small detectors to bigger detectors, and we started moving them closer, and our solid angle started increasing. By the time we got to the early 80s, we're up to almost 1%. A little bit longer, mid 80s, up to 2%. Late 80s, early 90s, almost 10%. A little bit later than that, we reached the 50% level. Okay, 50% level is good, but we have to make sure that it's actually a real 50%. So if we have a detector in between the pole piece and we have our sample in, what we have to realize is that if I can use a small detector or a large detector, which is right? A larger detector, in theory, gives you a bigger collection solid angle, but it doesn't always work because sometimes the detector is so large or the geometry is wrong that it's actually blocking the detector. Okay? Why do I want a bigger detector? Or why do I want a bigger collection solid angle? Let me give you a real example now. Okay? This is the signal measured from a test sample. It's a germanium test sample, but let's not worry about that at the moment. And I'm going to put the test sample in a, let's see now, was this 200 kV? Yeah, 200 kV microscope. Known beam current, known signal, 60 square millimeter detector. That's a pretty good size detector. And I'm going to measure that signal and call it unity. That's for a single detector. Let's look at the kind of microscope you have, a quad detector. The quad detector, 430 squares, that's what the Super X geometry is. And again, this is real data, is almost 4 times better. Not quite 4 because the 60 isn't really a true 60, part of the signal is blocked, but we're getting a bit better. There's a new geometry of detector. We call it the X-pad. It's something that we designed and built at Argonne, and it improves on both of those by a bit. It could take us from what on a single detector was 1x, a factor of 22. Now, think about that. You're now measuring something 22 times faster or 22 times more efficiently. So what does it mean you can do? You can do an experiment quicker or you can do an experiment better. You can never do both. You take your choice. Which do you prefer? Do you want to spend more? Do you want to do it faster, spend less time, and keep the statistics the same? Or do you want better statistics with the same amount of time? Okay? Historically, how have things happened over the years? This first red dot is the first detector that we put in on the Joel microscope at Illinois. Over the years, these are single detectors. Single detectors have reached the limit. They've saturated. They can't get much better. Array detectors, either dual detectors or quad detectors. The quad detector is about here in the system. And they've gotten a little bit better, and that's XPAD again, okay? So it's gotten a little bit better, and I will tell you all, it has a Guinness World Record. It's the most efficient X-ray detector in the world. And that's a real certificate hanging on my wall in the lab. The lab doesn't care about it, but I did. All right. In addition to just getting a detector in, we also have to worry about the sample holder, okay? So we put a detector in, we have a sample in, and here's part of the reason that all the detectors aren't as efficient as this. The side walls of the holder can block X-rays from going into the detector. So in the diagram here, even though I've got a nice big detector in, it's really close, I've shaped it just right, because of the sidewall, it would block all the signal, okay? And so how do we solve this? Well, typically in your microscope, you used to tilt the holder, okay? And as we tilt the holder, you see the signal going up and down. Why is that happening? It's happening because the penumbra, or the shadow that's cast on the detector, is changing, okay? We can model that, okay? If we have a general geometry, we have a detector on the side of a microscope. If the sample is flat, we put the detector in, we're going to get one signal, okay? As I tilt the holder toward the detector, what's happening? That shadow that's being cast is starting to decrease. The signal is going to go up. It's going to reach a point where we're now at 100%, and it'll be flat. We can also go the other way, right? Start tilting backwards. Now that shadow starts getting better. The signal's going to decrease. It'll hit a minimum level and then start increasing again. Because now we tilted so much, we're actually getting signal from the bottom of the detector, or bottom of the sample. Okay? Knowing this for your microscope is important. Okay? I'm not going to tell you I'll give you the quick and dirty way of measuring it. What you do is you put a sample in the microscope, known geometry, center everything, and just measure the number of counts as a function of beam current as you tilt the sample. You're going to see something that looks like that. You look at that and you say, but Nestor, that doesn't look like that curve. And the reason it doesn't is when you put your sample in the microscope, it's flat. As you tilt your sample, what's going to happen? The thickness of the sample is going to increase, and it's going to increase by the cosine of the tilt angle. Okay? So if you took this signal, corrected it for the cosine theta tilt, you're going to get that signal. That looks just like the previous curve. And in fact, there's an experimental measurement now for a single holder tilting. We see we've gone through, we've got a flat zone, we've got a minimum, we've got a back zone. Why do I want that? Well, the best signal that you're going to measure is somewhere up here. You need to know where that point is. What's that cutoff angle? It changes for different microscopes. Let's skip that slide. That's what sample I used to do it. Here's an example of that measurement done on a whole series of different microscopes. Look at how much it varies. Okay? That cutoff angle in this microscope is at 0. That's great. Okay? This one goes up to 20 degrees. That one's about 10. This one is again 20, but it's got a huge flat zone. And notice also it varies depending on the design of microscope and also type of holder. Okay? It also varies depending on how many detectors you have. Here's your microscope. You've got a Super X system. You have 4 detectors in your microscope. If you look very closely, there are actually 4 traces here. 2 in green and 2 in red. Okay? You have 4 detectors, 2 at the front, 2 at the back. All 4 detectors are different, slightly. Why? Because they have a different view of the specimen. And you notice when we tilt it toward one set of detectors, we're tilting toward the green detectors, that signal's going up, while the signal for the red detectors, the other side, is going down. If we take the sum of all of this, that's the curve response. So for the geometry that you have here at IIT, the best possible geometry is for the flat sample. Okay? If you tilt it back and forth a little bit, by about plus or minus 10 degrees, it doesn't change much. But as you tilt higher and higher, which you can in your microscope, realize that the signal is going to be dropping. Also realize that while one detector is getting better, the other one's getting worse. Okay? So, quad system, you want to be flat if possible. If you're tilting, can you do a work? Yes. Nice thing is, it's a pretty symmetric shape, so we can predict that. All right, let's leave geometry for a moment. And let's ask ourselves, why are we doing EDS? We're doing EDS because we're looking at something, and what we want to do is make a measurement. And when we make a measurement, what do we want to do? We want to maximize the sensitivity, minimize the time. So how do we maximize this analytical sensitivity? What's the important parameter there? The important parameter there is the detectability limit. Now, we can mathematically define what a detectability limit is. We can use the student t-test criterion. We can say that the change in the signal has to be greater than 2.33 times the square root, times the statistical uncertainty, and that's just simply the square root of the intensity plus the background. Okay? We can then say, take the ratio of that to the raw intensity, and we have a general equation. Okay? We can simplify that general equation even further. We can say, what's the minimum detectable mass? The minimum detectable mass is when, if the background is very low, and so B is very much small, then we just want to measure an intensity. The minimum detectable mass goes inversely with the intensity. Inversely is the square root of the intensity. If this is the minimum detectable mass, the minimum mass fraction is the other way around. It's when the background is actually much higher than the intensity. So the equation changes a little bit. There, instead of inversely proportional to the intensity, it's inversely proportional to the product of the intensity times the peak to background ratio. What does that tell us about our geometry? How do we increase our minimum detectable mass? The smallest thing, we want I to be as intense as possible. When this is as large as possible, this is as small as possible. When we want to do the minimum mass fraction, it's not just I, but it's also B that comes in. All right. And that's not a traditional way of doing it. Why is this important? It's important because the characteristic intensity emitted from a solid, the I, is isotropic. Goes out over 4 pi radians. Background in our microscope is highly anisotropic. That's because, remember, it's created by the electron Bremsstrahlung, which is anisotropic, it's highly relativistic, and the discussion of that is really complicated, and we don't have time to talk about it today. That's a whole other topic just by itself. The important thing to realize is, can we get very good minimum detectable masses today? The answer is yes. We maximize that intensity. You have 2 parameters there. You can make the minimum detectable mass as small as possible, which means the best, by either maximizing the intensity. If you can't maximize the intensity, you can increase the current or increase the analysis time. All of those make the minimum detectable mass smaller. Why not just make more current? Because some samples get destroyed with more current. Why not just keep the current constant, keep the intensity constant, count for a longer time? Again, you can do that, but some samples destroy with time. So what I want you to realize is you have 3 parameters here to use at your disposal to do your experiments. Amount of current, the amount of time, or the type of detector that you use. And you want to maximize any one of those. As long as you maximize those 3 for your experiment, you're getting the minimum detectable mass that you can get. All right, let me show you an example of that. Let's go to steel. This is a carbides in steel. You see the dislocations in the carbides. I want you to first focus on there. And again, we see tiny precipitates around there. If I do an analysis, and I'll call this a map for a moment. It's a hyperspectral image. We can see the silicon carbides. We can see the moly chrome, so these are M23C6, silicon, chrome, moly. And what we see coating the dislocations now are very tiny amounts of niobium. So it's niobium carbides coating those. Now, could we have told that by doing a complex diffraction contrast experiment? We could have done diffraction, done diffraction, do the contrast analysis, do a full-blown dynamical experiment. We'll get results. By measuring the lattice parameters, you can tell it's a niobium carbide or something. Now, on the flip side, I didn't want to do that. I'm getting tired in my old age. I said, well, I'll just do a map to see what's there first. And that's what I did. I just did a map. Now, how long did that map take? This is done on my new system, okay? So, 400 picoamps of current. That's not a lot of current. Most people run a lot more. But that, for me, is a lot of current. I tend to run about 100 picoamps nowadays, 100 to 30. I did a square image at 2,000 by 2,000, and somewhere it told me how much time. Yes, 13 milliseconds per pixel, and I got that. That's the signal, okay? Now, it's also a 2K by 2K image. So 2K by 2K, even at 13 milliseconds per pixel, takes a long amount of time. But that's not a hell of a lot of time with the new detectors. Now, go to the conventional detectors, which are 20 times less efficient, like I showed you in that earlier slide. It's going to take you 20 times longer, or you'd have to spend 20 times the time there. All right. Here's another example of using an efficient detector. This is an automotive catalyst. Oops. That image was supposed to be, oh well. It was supposed to be a black and white image. Maybe it's, forget it. It's the color one. It's the final image. It's a palladium, calcium, titanium, cerium, zirconium. There's a catalyst in there, and you weren't supposed to see the yellow yet. That's the actual catalyst. So what can we do with that in a conventional machine? So here's the image of this area, just looking at the palladium with a detector that has a solid angle of 0.2 steradians. That used to be a good detector. I spent 10 microseconds per pixel, so it took roughly 2.5 seconds to take that data. What do we see? Nothing. Spots and dots. All right, let's do a new detector, same area, same thing, but 0.7 steradian. This is the Super X now. I'm starting to see something there. Oh yeah, that looks like it was real. Again, 2.5 seconds to do that. Now let's go to a little bit better detector, or to a full pi steradian detector. Okay, that one we can say, yeah, was there something there? Yes, but in 2.5 seconds I've now seen, can show you what's there. So does using the right detector and the right experiment matter? The answer is yes. All right, one other thing I want to talk a bit about is the microscope and detector as a system. Now, we talked a lot about on the first day what a microscope is and all its components. We talked today a lot about the detector and its components and how it works. But in reality, what you have is an analytical system. It's not just a microscope, it's not just a detector. We put the two together, okay? So it's important to understand how those two react with each other and what artifacts are created by merging the two, okay? So now let's look at that particular spectrum. It's a spectrum from a piece of steel that I stuck in my microscope. What's the biggest peak we have there? Copper. There's not that much copper in my steel, okay? What's happening there? Well, remember, we put a sample in, we have a holder in it, and we're not only seeing what's in the sample, but we're seeing the immediate environments, okay? All right? So the complex geometry that we have today is the fact that we have a microscope with components, we have pull pieces, we have objective apertures, we've got holder material, and we have a detector that not only has a large collection solid angle, but it also has a very large subtending solid angle. What does that mean? Is if an X-ray is generated from here, if there's a line of sight path to that detector, it'll detect it. How do we minimize the subtending solid angle? We really have to design that collimator right. Okay? Back in the good old days at Illinois, when we had a single detector, we designed our own collimator. It was a very good collimator. The system peaks were low. But nowadays, when we have very complex detectors, so there's a collimator on the front of a detector. You notice it's really small. So it's got a good collimation. So because it's got a good collimation, it's looking at mainly only the X-rays that come from here. There's a zero collimator on this detector. It's a naked detector sitting out there in free space. So it will see any X-ray that hits it. Take that black area away. An X-ray that's created there will get in. An X-ray that's created here will get in. So we'll see this immediate system environment. Okay, so knowing what your system is made up of, knowing where the iron, the cobalt, platinum if you've got an aperture, copper, tin, moly from the holder, aluminum, silicon, zirconium if you've got an aluminum collimator. Also important, not only are we getting signal from this, we're also getting signal from the detector itself. The modern detectors today, I told you already, are very thin. Okay? They're so thin that the X-rays go right through it. We talked about that in terms of efficiency. Well, X-rays that go right through the detector hit the stuff that's behind it. If they hit the stuff that's behind it, you'll get X-ray fluorescence of the material behind it, and you'll actually start analyzing the composition of your detector. Or actually, more precisely, the composition of the material behind the detector, which, for example, in modern detectors, remember I told you they all have Peltier coolers. The Peltier coolers have insulators behind it, so you will frequently see information of the Peltier coolers. Depending on how old your detector is, at one time, a lot of the detectors today are made in Germany by a company called PN Sensor. They used to use a lead solder to put the detectors together. They don't do it anymore because it's now against German safety rules. But you will sometimes see lead peaks if you have a very old system. Another manufacturer used a lanthanide as part of their insulator for their Peltier cooler. Another one now uses yttria stabilized zirconia. You'll see yttria peaks. Okay, so know where they're coming from. Can we minimize this? Yes, we minimize it by manufacturing things around the sample, trying to minimize things that generate X-rays. So for example, in this case, what we did is we rebuilt the holder, minimized the amount of copper, and now the copper signal disappeared. Let's see now. We also, how do we do that? We surrounded the sample by beryllium. Okay. The other thing that happens, and you will see this in every microscope I've ever used, put a sample in, a fresh sample, take an image, everything looks fine and dandy, and then I focus my probe down, and I get this nice little round mound of carbon contamination, focus probe. We can mitigate that. Where's it coming from? It's diffusion across the surface. Okay, you've made your sample somehow. You've touched it possibly. You've cleaned it with solvents, or it's just dirty. Okay. So we want to mitigate this. One way of mitigating it is to remove mobile hydrocarbons. We can do that with a plasma cleaning process. So here's an example piece of steel where I've focused the probe down. So here's those focus probes. I now treated it by doing a plasma cleaning. The plasma cleaning basically introduces ozone to the sample. Okay? That ozone reacts with the mobile hydrocarbons, forms CO. The CO pumps off. Okay? Now, so you can see here's one before treatment. Here's after treatment. There's still a little bit left. If I do yet a further treatment, it's all gone. Okay? That sounds great if your sample can take plasma treating. What happens when you're doing carbon? So here's a carbon film with a two-dimensional polydiselenide material on it, fresh. I put it in my plasma cleaner because it was starting to contaminate, and we're starting to deteriorate the carbon, deteriorate even more. Now, what happens if your sample is carbon? There's somebody here that works on polymers. I don't see him. Oh, there he is. There's our polymer man. So plasma treating a polymer is difficult. There's another process called UVC treating. Maybe we can talk about that later. Okay. It still involves ozone, but it's more gentle. All right. Don't forget you have to prepare your sample to put it in the microscope. Lots of ways of preparing sample. You can do electrochemical polishing. If you do electrochemical polishing, you have residual polishing solution. In this case, we used hydrochloric acid. There's a chlorine peak from the hydrochlorine. It wasn't completely washed. If you do ion milling, okay, you can get sputtered material from the area around the sample that redeposits on top of the sample. Or you can even get some, this one you can't see the argon. There's an argon peak too, and the argon's deposited. Everybody, I don't want to say everybody, a lot of new people like to use a focused ion beam system to make their sample because, oh, it's really quick and fast, it'll make a beautiful sample. And yes, you can make a nice thin wedge, but if you're not careful, you're also depositing, if it's a gallium fib, you're depositing gallium on the sample, on the surface of the sample. So they'll do trench mode, do lift outs, make a nice thin area. Yes, that looks beautiful until we go in and actually do an analysis and see there's a very large gallium peak there. Okay. Now, if you do it right, can you minimize that gallium? Yes. Can you clean the gallium off? You can get most of it off, but you don't always get all of it. And you're also implanting gallium in your material. Let's see, what's the next one? So here's one new graduate student working with me. Oh, I got a beautiful sample for you. Look I can see this structure. And I said, okay, let's see where the gallium is. And the gallium went all the way across his beautiful structure. So there's gallium everywhere. All right, be careful of that. Some of you will take samples and put them on grids or supports. Remember that when we buy a grid, and we can buy grids of different materials, going anywhere from beryllium grids all the way down to gold grids. If we get scattered information, X-rays getting scattered, they will excite the grid, so we will see these elements. I tend to like either a pseudocarbon or a diamond or silicon nitride grids. They're pretty good. Remember, when you buy a carbon film, you're not buying carbon. It has carbon in it. It's mainly carbon. But if you actually analyze your carbon film, it not only will have carbon, it'll have oxygen. It usually has phosphorus. You might see some argon if they've done it by a deposition process. And you'll have mobile hydrocarbons all over it. So your carbon films aren't carbon. I tend to use silicon nitride films. Again, they're not pure silicon nitride. You buy them. They're mainly silicon and mainly nitrogen, but there's always a large oxygen component, and there's usually always a little bit of chlorine because of the way they make the silicon nitride. They use a silicon chlorine compound to deposit the silicon, and then they use ammonia to get the nitrogen, and they react it, and they get a silicon nitride, but it's not true silicon nitride. Okay, the last thing to remember, if you're using some kind of support system to support your sample, remember where your sample is, where your detector is, and is it possible that the X-rays from your sample get intercepted with your grids. So this would be, if you have a detector up here, this would be the absolute wrong way of mounting a sample. I'd flip this over the other way around so the film is on the top side relative to the detector. I would also avoid trying to analyze anything right next to a grid bar because the grid bar is going to absorb or stop the X-rays. Fibs are equally bad. I personally hate it when people mount a sample on this side of the grid bar because what's going to happen if I have an X-ray detector on this side, the X-rays aren't going to go through that. Now, could one make a sample where it's mounted there? Yes. Could you use a different procedure? Like instead of mounting it on a copper grid, mount it on a silicon disc where it's sticking out over the edge, and now we have free access. More difficult, more costly. Make something simple first, test it, use a grid, use a carbon film, learn how to make the samples, and then when you get to the point that you really know what you're doing and know how to make the samples, then spend the time and make it the right way in the right geometry. All right, how are we doing on time? About an hour, okay. As usual, I underestimated the amount of time it's going to take for me to talk. We're going to go for at least another half an hour and then take a break, okay? All right. What kind of spatial resolution can we get doing analysis? That's an interesting question because spatial resolution means different things and how you're measuring. Are we worried about geometrical broadening where we've got a probe that's focused and we focused it to a point, but as it gets out of focus, it's going to broaden again? Are we going to get beam broadening due to inelastic scattering? Are we going to get chromatic broadening, inelastic delocalization, or image and diffraction delocalization? all of these contribute to the resolution of our experiment, okay? It's important to know how each of those contribute to your measurement. Let's take a simple-minded view first. The simple-minded view is if we had a bulk sample and an electron beam comes in, it scatters through it. Our simple-minded view of why we're going to the TEM is we're going to cut off all this inelastic scattering by chopping the sample. If we chop the sample, our broadening of the beam as it scatters through the sample is going to decrease. There's some simple analytical formulas. They're very simple. They're not accurate, but they give you an order of magnitude estimate of the kind of broadening you're going to get through different materials. So that's the Goldstein formula for calculating approximate broadening. Okay. You notice it goes inversely with energy. So higher energy, less broadening. Increases linear with Z, and it goes as the thickness to a power. Okay. Gives you some numbers. Nice low Z material like carbon, depending on how thick it is, we got relatively low broadening. But now let's take that same material and not be carbon but gold. You notice the broadening starts increasing dramatically. And at this point, the model for this simple broadening equation doesn't valid. Instead, we can do Monte Carlo calculations. There's plenty of programs out there that you can find that'll do the calculations. And they'll trace a beam going through a solid. And they'll give you better estimates of the thickness. So I've done the same calculations as the previous ones. And now we've got some numbers here. But importantly, I want you to see what we're looking at. When we start talking about samples that are 100 nanometers thick, which is a routine sample for us, we're getting substantial broadening as a function of atomic number. Okay? But I can get an atomic resolution image. Is this really atomic resolution? Well, if your sample's infinitely thin, can we get atomic resolution EDS? The answer is yes. Here's a single atom of silicon sitting on top of a monolayer of graphene. And there's that single atom, and there's the silicon peak. Do we have atomic resolution of X-rays from that? The answer is yes. Okay? Now, can I get something else? Let's go to my favorite material, nickel aluminum. This is the first material I got introduced to by a certain person. It's actually some of his single crystals from his PhD thesis, which I still have. And I still make samples out of it. So nickel aluminum, if we look down the 001 axis, has an interatomic spacing of about 28 picometers. We can put it in our atomic resolution microscope. And for those of you that, if the room lights are a little dimmer, you can see periodic structures, and we can see two different types of atoms. Remember I told you in high angle dark field STEM, the contrast is proportional to Z. So we've got a bright and a darker one. The bright one is nickel. The slightly darker one, or not so bright one, will be aluminum. If I do that same measurement now and turn on my X-ray detector, that's the signal I'll get. Again, a single frame, 50 picometers, 400 microseconds per pixel. Am I getting something that looks like atomic resolution EDS? The answer is, I'll say, yes, it looks like atomic resolution. Don't ever call it atomic resolution EDS. That's a mistake. It's an effective electron channeling going through the solid. I can do it in lots of different materials. Here's gallium arsenide. I can show you gallium versus arsenic, okay, which is even a smaller spacing. That the other one was 280 picometers. This was 140. Okay, but remember when I put the probe on the gallium, because there's a finite thickness, that probe is not only exciting the gallium, but it's also exciting a little bit of the arsenic next door. So we will actually get arsenic signal when my probe is on top of the gallium. Is this good enough to say that this is gallium arsenide? Yes. The important question is, what is the question we're asking? So here's another example. This is some work with Les Allen and company. You remember this one, right? All right. And this one's a better example than the one I just showed you. So strontium titanate, another classic example that everybody uses to say, look, I have atomic resolution. Let's stop the probe right on top of the colors have changed here. Green and blue are supposed to be the same. apologize. This one should be, the blue there should be blue. This one should be blue to match that one, or this one should be green. Okay, we stop the probe on top of the titanium peak. So there's the blue signal here. Notice we're still getting a lot of strontium. We stop the probe on top of the red, which is strontium here, the red signal, we'll still see titanium. Okay, what's happening here is the beam is channeling through the solid. Okay, and we're exciting not only the atom we want, but the neighboring atom. Can we analyze this in terms of atomic resolution? Yes. As usual, I have more to say than the amount of time that I think I'm talking in. So I'm going to, you all have lots of slides in the handouts. I've skipped lots of material, okay? And I'm probably going to even skip more now. I'm going to leave the hardware, I'm going to leave the artifacts, and we're going to go into quantification next, okay? The important thing about quantification is you're going to have a spectrum. That's data. First thing you want to do is identify all of the peaks in your spectrum. Make sure you know what's there. Make sure you know what's part of your sample and what's an artifact. We talked about all of that. The next thing you're going to want to do is you're going to want to measure the intensity of a line. Okay? What I want to remind you is when you're measuring the intensity, never measure the peak height. I always want you to measure the peak area. Okay? The reason for that is very simple. I told you already that these detectors have a variable energy resolution with energy. Okay? That means two peaks, even if they're of equal intensity but at different energy levels, will have different widths. So the amplitudes will be different, but the integrals will be the same. And it's the amplitude times the width of the peak that gives you the intensity. So all peaks, these two peaks are identical in terms of integral, the total number of counts. But the amplitude of this one is a lot less than the amplitude of that one. Never measure peak amplitudes, always measure integrals, okay? Backgrounds are complicated devices. I told you a formula before for background. There's a lot of computer programs that do modeling the background for you. Here's a nice model. You notice it works really well out here. It's a model I used years ago, but it tends to break down at very low energy end. There's nothing you can do about that because there's so much complicated stuff going on here. Theoretically, that's right. Practically, it's an issue, but we'll find out later that analyzing things down at this low energy end are difficult. If you're going to do a background, I don't care what model you use. The important thing is, does it accurately represent the background under a peak? I'm very happy if you just use a simple linear fit between one side of a peak to another. Okay? That's an accurate background measure because the statistical error you're going to make there is relatively small. Okay? The last thing is almost all the manufacturers give you a computer program or sell you a computer program and they say, yes, we can fit all the peaks. They'll have multiple peaks. You'll tell it what elements are present and it'll fit peaks. The important thing, what they're doing is they're not actually fitting the peaks, they're fitting the profile. Okay? And they're saying, I'm going to give you some peaks, you're going to tell me what elements are there, and I'm going to make it match the profile. Make sure of several things. First of all, does the peak fitting work for your material? Are your peaks calibrated? Is your detector calibrated? Because all of the systems nowadays assume you have perfect calibration. I will guarantee you that after a year or two of time, the calibration of your detector will change. But your computer program won't. It'll think the peak is here, and you've had a small shift to the peak, the integrals will be wrong. Okay? Check the calibration, look at the peak fits. Do they actually match your data? 2 weeks ago, I was at U of I. We were doing a live test. We acquired a spectrum. I said, okay, let's just do a peak fit. And a beautiful peak of experimental data, but the peak fit showed the peak was way over here. So the calibration drifted, nobody had checked it in 2 years. All right. There's a lot more things in the notes about peak fitting and analysis. We're not going to talk about that right now. What I want to talk about really now is move into quantification. Because let's ask, first thing is, what's the question you're asking about your sample? Do you want to know, and what kind of result do you need? Do you just need a qualitative? What's there? Do you want it semi-quantitative, or do you want to be full quantification? In order to do that, what do you need to know about your sample and the spectra in order to quantify it? Okay. So did you plan your experiment right? Is the instrument calibrated? Do you need a standard, yes or no? You sometimes will. Did you prepare your sample properly? Did you, oops, that's a spelling error, sorry. Know your instrument, know the facts and artifacts, we talked about that just now. Do a survey of the specimen, optimize the parameters, collect the data, and then attempt to quantify. All right, so now we're going to talk about how we quantify. And I'm going to talk about quantification in words first, not an equation. So, the number of X-rays you detect is simply the number that are emitted by the sample times the efficiency of collection, solid angle, efficiency of detection, the efficiency of the detector. So we talked about these two before. What we're worried about is this: how many are emitted? Well, the number emitted are first how many are generated, plus the fraction that actually leave the sample. Not all the X-rays that are generated leave. How many are generated? It's the number per atom per electron times the number of electrons, beam current, times the number of atoms, area times thickness, times any other X-rays that are generated by other sources. And finally, this one, the number generated, is the number per ionization event times the number of X-rays per ionization event times the fraction of the total that you actually measured. So all of this in an equation is here. There's the equation that describes all those words. And that's for a bulk sample. Now, these can get really complicated. You see, I'm integrating things over path length and whatever. In the TEM, we can make several assumptions. First of all, we're going to make the assumption, remember, that's a thin sample. So I'm going to cut off it. I can assume if it's a really thin sample, there's almost no energy loss, no absorption, no scattering. And then that means that this complicated equation changes to something relatively simple. Still has a lot of parameters, but it's a lot simpler. There's no integrals anymore, you see. We have an area for a very thin sample that's related to the probability of an X-ray per atom per electron ionizing, creating, times the number of atoms, times the number of electrons, times the efficient probability of detection. Okay? So, 3 parameters that control everything. If I measure that, that's what we measure in our detector. If I know the beam current, the thickness, if I know my collection efficiency, I can get these values. Let's assume I can get that. Then I can solve this equation for composition, right? We just take this, and this. To that side of the equation, composition equals that divided by all the other stuff. Sounds nice and simple. But what's the complication there? In order to use that equation the way I just told you, you have to accurately not only measure the intensity, I have to accurately know the beam current, the amount of time, and the thickness of the sample. Do you know that for your sample? Do you know that for your microscope? 99.9% of the time, the answer is no. So how do I do quantitative analysis? Well, there's a trick. And knowing all these parameters is also not simple. So we can just to give you a sense of things, that's how the cross-section varies. It's a function of atomic number. It's a function of energy. The radiative partition function, K alpha to K beta ratio, changes with atomic number. The fluorescence yield changes with atomic number. The detector efficiency varies with energy. The amount of X-rays you get varies with beam current, and it varies with thickness. All of these vary. So using that last equation, this one, is problematic. It can be done. A good physicist would do that. He would just sit down and measure everything. Now, is that practical in the real world environment in solving real problems like you do? That's really a lot of work. It can be done, but there's a simplification we can do. Okay? And so instead of knowing all of these parameters, what we can do is go back to this equation and say, Well, first of all, that tells me the intensity of element A in that sample. If it's a pure element, we're done. Right? We measured, I want to know if this is aluminum. I want to know if this is gold. Simple. You never do that. We've got a titanium aluminum alloy, for example. Okay? So what are we interested in? We're interested in the ratio of titanium to aluminum. That tells us the composition. All right, so we're going to measure the intensity of the titanium line, and we're going to measure the intensity of the aluminum line. Think about this for a second. Instead of looking at the absolute intensity of an element, let's instead look at the ratio of element A to element B, titanium to aluminum, okay, for example. Write that previous equation, but take the ratio. That very complicated equation becomes very simple now. That simplification says the intensity ratio, IA to IB, is equal to some constants times the composition ratio. All the parameters, specifically beam current, sample thickness, a few other parameters, drop out. There's still some physics related into these constants, cross-section, flow ratio, radiative partition function, but that's a nice simple equation. Intensity ratio equals some constant times the composition ratio. Okay? That's a nice, easy way of getting quantitative analysis. Because generally what we're interested in is what's the ratio of 2 elements or 3 elements or whatever. Okay? So how do we do this measurement? We do it 2 ways. We measure this, we know the constant, we can determine the composition ratio. How do you determine that constant? 2 ways of doing it. You can do a first principles calculation. We know what all the parameters here are. It's these terms. I just showed you in the previous slide. We can calculate all of those. So if we, if we measure this, we can calculate all of that, we can get that. Okay? The other way to do that is make yourself a standard. Make a standard of something that you know, a titanium aluminum standard. You know that. You can measure that. So you know that, you can experimentally have that value. And now you've got a calibration for your microscope for this composition alloy. Those are the 2 ways of doing quantitative analysis. 1, measure this, calculate this, and determine that. Second one, make a standard, determine that constant, and then use that constant times the intensity ratio to determine your composition ratio. Those are your 2 methods for doing quantitative analysis. How accurate can this be? Okay, let's do the calculation method first. Okay, we want to calculate all of these parameters. Okay, can we do this calculation? Here's a calculation of that factor. Okay, it's called the K factor. Okay, here's a calculation, and you notice there's a lot of variation in that calculation. What are the main variations for that? The main variations for that happen to be in this term right here, the ionization cross-section. Okay? Over the years, there have been a lot of different models for the ionization cross-section. You might say, well, it should be a fundamental. We should know it. Well, we know the basics of it. We also have experimental measurements of the ionization cross-section that have happened over the last 100 years. No, not quite. Yeah, close to 100 years. Okay? But there's errors in those measurements. There's errors in the models. Not everybody does a full relativistic correction for these. When the kind of energies we're talking about are relativistic. Okay? Some of the measurements are heavily relativistic. They're done at not hundreds of kilovolts, not millions of volts, but tens of millions of volts. Now extrapolating those back down to low voltage is problematic too. So, how close can we get to a measurement? How good of a calculation can we do? Well, here's the solid dot, which ones are the experiment? The big round circles are the experimental K factors. And then the different lines are different fits to different ionization cross sections. This is a hard curve to look at. This is the same data, and all I'm doing now is taking the difference between the model and the experiment. Okay? And you still see scatter, but the important thing I want you to see is that scatter is about plus or minus 10%. So if you're using the ratio method and experimentally and calculating the theoretical K factors, what kind of error can you expect? You could trust it to about 10%. You want to do better? Make yourself a standard. Make a standard, then you will have the K-factor for your instrument. Oh, I've made a K-factor measurement for my instrument. I'll give it to my friend who's got the same instrument somewhere else. Doesn't work. You have to do the individual measurement for the system, because in that K-factor, the experimental factor, is the operating parameters of the microscope, and importantly, the type of detector you have. No two detectors are identical. Some of them are pretty close, okay? Other ones aren't. Now, you say, well, but manufacturers show me things all the time. Look at how accurate our analysis is. Let me show you one of those. Oops, I'm going the wrong way, sorry. Here's a round robin test that was done. 12 different laboratories on a piece of steel, okay? You can see the scatter in the information. You can see the scatter is only about 1%. Why is this so good? Nestor, you just told me there's a 10% error. I'm showing you data that's 1% error. I was part of this experiment, okay? Why is that so good? Two very simple reasons. A, they chose the right sample. They chose a piece of steel. And what did they ask you to analyze? Nickel, chrome, and iron. Next door neighbors in the periodic table, okay? The correction factors are near unity because they're next door neighbors in the periodic table. They're high energy lines up in the 6 to 10 keV range. The efficiency is almost 100%, regardless of what detector you got. This is the perfect case to prove that I can do quantitative analysis. I can do it on any system if I had these parameters. Let's take something more difficult. Let's not pick next door neighbors in the periodic table. Let's pick something that's high Z and low Z. Far apart in the atomic table, far apart in detector efficiencies. A good example of that is nickel oxide, NiO. We can get single crystals of nickel oxide. Do the same test again. NiO, these are the results of the composition spread. Now look at that variation. Okay? Some guys all got the same result. Other guys that started to deviate by easily plus or minus 10%, some even worse. What's going on here? What's going on here is we've got a nickel line at near 100%, an oxygen line right down here, right where the detector efficiency is changing a huge amount. Okay? So, can you get good quantitative analysis? Yes, if you pick the right system, if you understand what you're doing. If I wanted to do nickel oxide quantitation, and if I didn't know I was one of these guys, because I knew what I was doing, but one of these, could they have done this? The answer is yes. But now these results determine their K-factor. And you could say, this is what I measure for the nickel-oxygen ratio. That's my correction factor. Then I can get the right answer, because I knew the sample ahead of time. All right, so can anybody do quantitative analysis? Yes. Can you do it accurately? Yes. The more accuracy you want, the more important it is for you to make yourself a standard. Okay? Nestor, I can't make a standard of my sample. I got some weird hafnium, tantalum, lead, perovskite, halide, something or other. I can't make a standard of that. Okay, then you're going to have to do a calculation. What should you do? You should first try a few standards, something like a steel, something like a stable oxide. Do a measurement, compare it with the calculation that you get for your system. If your calculation is giving you the right answer for several different standards, not just one, don't use steel. Pick a steel for one, pick an oxide, a silicide, something with large variation in atomic number. If your calculated models give you the right answer for the standards, then at least you can trust it for your unknown. Okay? So that's the methodology I use. I have several standards that I run, some of which are very old, like nickel aluminum, some nickel silicide, some of the titanium alloys. We can make the standards. We may compare the results from the modeling program to the experimental values. If they work reasonably well, then I trust it a bit on the unknown. But I still have that 10% error that I worry about.
So the ratio method would work with the cave peaks, not with the other one.
No, it works with everything.
Because your detector efficiency goes down low.
Well, yeah, but that's why you make a standard.
That's
Okay, so you make a standard. I don't care. You notice I didn't tell you which line I used. So, oops, sorry. So you prepare a standard. It's called the K factor, but that's just because it's a constant. Okay, it could be a K and an L. It could be an. It's harder to do an M. And in fact, would I want to do a calculation for the M? The answer is no, because those cross sections are known even less than the K's or the L's. The most confidence you have are K to K. The next one is K to L. The least is K to M. Okay, but if you have an unknown and you can make yourself a standard and measure those intensity ratios, then you're fine. Okay, so there's a lot of places that you can look up the values. There are other places that you can look in the references to get cross sections. I trust Inakudi very highly. This guy I trust a little bit. And there are other ones in there that you can use. Check your computer programs that you have with your instrument. What do they use? Some of them allow you to do experimental K factors and put them into the database that they have on the microscope. Other ones say, oh no, we know what we're doing, we'll do it all for you, but they won't tell you what they've done. Okay? That's very dangerous. Okay. Is there another way of doing the analysis? The answer is yes. So we said we've had an unknown, we just measure the ratio of two elements, and a lot of terms drop out, and we can measure the intensity ratio that gives us the composition ratio. You could also take your unknown and compare it to the intensity in a standard. Now, when you do that equation and do this time element A and an unknown, element A and a standard, a lot of other things drop out. Cross-section drops out, fluorescence yield drops out, a lot of other parameters will drop out. What you're left with is the intensity ratio is equal to some constants times the composition ratio, same equation, but what you have to know now is the composition in your standard. More importantly, you have to know the thickness of both samples, and you have to know the beam current in both samples. Can this equation be done and used? Yes. It has been used for years. The Lehigh group uses it a lot. They call it the chi factor method. Okay? They measure the intensities. They rewrite the equations. The important thing in all of this, let's see if I put the right button here, is they're very dependent upon the detector efficiencies and the beam currents. If you don't know those, then you can't use the chi factor method. But it is a valid method and it works. And you can look up Masashi Watanabe's paper in Journal of Microscopy that describes it. It's a very nice method, it works. I personally don't use it, but that doesn't mean it doesn't work. And the reason I don't use it is requires always to measure the beam current. Now, yes, do I always measure the beam current? Yes, but I don't always know the sample thickness. Okay. Yes, the question was, how did I get the beam current? You have to use a Faraday cup, okay? Or calibrate your screen. And what I do is I have a Faraday cup and I calibrate the screen current so I can measure the screen current under the same conditions all the time, and it's calibrated. And I calibrate it for all my conditions. Each voltage is calibrated differently. All right, a few more minutes on EDS and then I'm going to stop and we're going to switch to electron loss spectroscopy. Okay. So, I told you a lot about quantification, and I sort of told you what the assumptions were. I said, oh, it's going to be a thin sample. What does a thin sample mean? A thin sample means no energy loss, no X-ray absorption, and no X-ray fluorescence. That's what a thin sample, and also no channeling. It doesn't say anything about the crystallinity of the sample. Are any of those always true? The answer is no. Okay. However, some of them don't matter too much. For example, the fact that the beam loses a little bit of energy going through the solid doesn't make a big difference. Why? Because we're operating up here at the high energy regime. The changes in the ionization cross-section are relatively small as a function of energy. And it's all comes into about that the cross-section is directly proportional to the relativistic energy of the beam, which is half mc squared beta. Okay? And a small change in energy loss makes only a small change in this, which makes even a smaller change in the ionization cross-section. So do we have to worry about energy loss for typical samples in an electron microscope? The answer is no. What else do we have to worry about? How about X-ray absorption? X-rays are generated, and you know all about X-ray absorption. We talked about it, about the detectors. You know about it in the doctor's office, right? X-rays go through material, they get absorbed. They slow down. So the intensity coming in is not equal to the intensity that's coming out. Okay? Why do we have to worry about that? Well, what we have to worry about is this effect. We've got a sample of a known thickness. It has a known thickness, and X-rays generated in there, and the X-ray has to get out of the sample. So what do we have to do? We have to know the geometry and then calculate the absorption of X-rays going out. You can write the equation for that pretty simply, okay? And we can write that out, and the important thing to notice is that's it related to something called the thickness of the sample, the density of the sample, and a factor called chi. Chi is the mass absorption coefficient of the sample times the geometrical factor. That geometrical factor depends on where your detector is, how high it's up, and how much your sample is tilted. These guys we can determine, okay? The thickness of your sample you can estimate, and you can calculate an estimated absorption correction, okay? What do we have to worry about? We have to worry about in the new geometries. In the past, we did this all years ago. We had one detector, so there was one geometry. Today, we have a sample, and we may have multiple detectors surrounding it. The correction factor for this detector, because the X-rays are going through this part of the sample, will be different than the correction factor for this detector that's going through a thick thing. What's the message here? Be very careful when you're trying to do an absorption correction. Can you do it? Yes. We have to know all of these parameters. We have to know our geometry very well. Well, how do I know when X-ray absorption is important? Look at this equation, this one. X-ray absorption gets important when the factor e to the chi rho t gets large. Okay? If e to the chi rho t is small, then there's no absorption. Okay? Oh, I'm sorry. So, I apologize for a moment. Can we include absorption correction in that simple equation? The answer is yes. Write it all out. Intensity ratios, a constant times the composition ratio, and there's a new term. This is the absorption correction term, and as I just told you, that absorption correction term is related to the mass absorption coefficients and an exponential term in chi rho t. So chi rho t is the controlling factor. If we know what that is, or estimate that, we can say, are we a thin film or are we a thick film? Do I have to do absorption or not? When is this important? When e to the minus chi rho t is a big number. So let's look at the value of chi rho t. If chi rho t is less than 0.1, then this number is near 0. The correction factor drops out. We don't have to worry about it. Okay? So, I've done the calculation for you in an approximate way. All right, I'm going to calculate this curve, and let's spend a few minutes on this curve now. This is a curve of the thickness in different atomic number materials where chi rho t equals 0.1. So this is chi rho t equals 0.1 for nickel K X-rays going through different atomic number materials. Okay? So if I've got a nickel K alpha X-ray in something that have atomic number 50, chi rho t, the value of t that we need to be 0.1 happens to be, let's call that 800 nanometers. Are we looking through an 800 nanometer thick sample? No. Take any one of these. What does it tell you? For nickel, do you have to worry, nickel K lines, do you have to worry about absorption in anything we look at in a TEM? The answer is no. You don't look often through an 800 nanometer thick sample. All right, let's change the energy of the material now. Instead of looking at nickel and different things, let's look at aluminum. All right, big drop, this logarithmic scale. Now if we're looking at aluminum in something that's 50, atomic number 50, now we're talking at something that's less than 100 nanometers thick. That's a typical thickness that we worry about. So in this case, aluminum, if we're worried about doing absorption correction, do we have to worry about it? Yes, in some materials, except when we get into this regime, right? Mid-transition metals, absorption of aluminum X-rays in the mid-transition metals isn't too bad, okay? We can get up to over 100 nanometers thick. And then, what about oxygen? Everybody wants to do light elements. Oxygen, no matter what material you look at, you're almost always going to have to do an absorption correction. So, can you do it? Yes. Do you know what parameters you need to know? Yes. You need to know the geometry, you know the thickness, you need to know where your detectors are. Okay? Low Z materials in high Z matrices, are you going to have to do an absorption correction? Yes. High Z materials in any matrix, are you going to have to do it? No, if you're measuring a high energy line. Nickel L line is close to the oxygen K line. So if the same calculation for the same material, but I was using the nickel L, I'd be down here somewhere. Okay? So, can you do those calculations? Yes. You have all the parameters, you've got references in the notes on how to do it, and there's a few computer programs around that'll do it for you. Again, most of the manufacturers will tell you they'll do an absorption correction for you. Check it. You don't know how they're doing it, what absorption coefficients are. Did they correctly describe the geometry of your microscope? Not all of them do. All right. And let me end on X-rays on this last example. So here are 3 examples now of the absorption correction in nickel oxide, nickel aluminum, and nickel titanium. Okay? I picked those very specifically because nickel is a relatively high energy line, about 7.5 keV. Titanium is about 4.5, aluminum is about 1.5, and oxygen is about 0.5 keV. If we have a straight line with no bending, there's no absorption. This is the absorption correction term is a function of thickness. Okay? And I've given you all the parameters that you need to reproduce this calculation. So, nickel in nickel oxide, at any thickness, do we have to worry about absorption? It's a straight line. The answer is no. Oxygen in nickel oxygen, for the initial state, very thin samples, no. But then as we start to get thicker, we have to worry about it. Let's move up a little bit in atomic number. Now, aluminum in nickel aluminum. Again, nickel in anything we don't have to worry about. Aluminum in the initial stages, we don't have to worry. Then this is dropping off. Again, it's X-ray absorption. Finally, titanium in nickel titanium. We almost never have to worry about absorption effects. So appreciate the difference, appreciate what lines you're looking at, and go from there. All right. I am going to end EDS now because we're just at 11 o'clock. I know we wanted to spend some time talking about energy loss. There's a lot more I would talk about in terms of EDS. I'll just walk you through all of these slides. And this was the abbreviated version, okay? I'm not going to talk about channeling. I'm not going to talk about spectral imaging. I won't talk about temporally resolved. I won't talk about lots of other stuff. I won't talk about tomography. Seriously, we probably should have done this for a bit more time. So I'm going to, I will, hang on. There is something I do want to say here. The last couple of slides are important. Everybody likes to make their life simple, okay? And one of the simple things that you will find that you will do, or at least I see a lot of students do, all I want is an X-ray map, all right? So you get a complex collection of stuff, and you make an X-ray map, and it's a beautiful color-coded picture. You say, okay, I'm done. I've quantified everything. My computer gave me this, and I know where everything is. I'm done. That's fine when you have major elements and high energy lines and there's no issues. Okay. I want to give you this particular example because I ran across it with a student in my lab just 2 weeks ago. So what we have are gold spheres, nano gold. Okay. And what the student was interested in, he's saying he's putting lead in the system. He said, I need to map out where the lead is. So he did his nano gold, he ran the computer program, and he told it to map out everything, okay? Okay, and what he was trying to do is get a quantitative map. And now all of a sudden he's got all these elements present, okay? Well, but this is gold. Where's everything else coming from? Where's the aluminum, the silicon, the sulfur? Well, first of all, is there silicon? He had it on top of a silicon nitride film, so that's where the silicon came from. But and if we look at this guy, where the hell is it? He didn't do me this is the important one, the sulfur. So hang on, let me go forward. Oop, wrong way. Yes, this was it. He was looking for where is sulfur or lead in his gold. And so here are the gold spheres. The blue was the gold, and the S was the sulfur map. Okay, sorry, it wasn't lead, it was sulfur. Apologize. He said, look there's sulfur surrounding all of my gold spheres. I found what I was looking for. And I asked him, how did you find it? He said, I did a map. So I said, okay, I'm not going to look at the map, because the map's the wrong thing to look at. I want you to look at the data, the raw data. Here is the raw data from that map, okay? Here's the gold line. That's where sulfur is supposed to be. Do you see sulfur there? No, okay? Why? How did this map tell me sulfur, but the actual spectra doesn't show sulfur? It's because the map is doing a computer analysis of the data, and the student told the computer there's sulfur there, so the computer said, well, here's my spectral profile. I'm going to do a fit, and I'm going to tell you how much sulfur is there to match this profile. So it puts the sulfur peak there because it's doing an integral across here and says, to make that integral right, I have to put a sulfur peak of so much. Okay? So it's a bad fitting program. But the map is drawn not from the raw data, but from the fitted data. So the map is telling him he has got sulfur. The spectra is saying, no, you don't. So what's my message? Don't trust maps. Is there gold there? Well, I looked at the spectra. Yeah, there's a big gold peak. Yeah, that's gold. Is there that little bit of sulfur? Is that really sulfur? No, it's not. Now, if you had sulfur, what it would look like, there is a sulfur peak, okay? You can see it's right in between those, the two gold lines. That's the gold M, alpha, beta, gamma, okay? And you can see if we go off onto the silicon nitride, back up. If I go to this area, which is just silicon nitride, yep, we've got silicon. There's a little bit of sulfur somewhere else, but there's no gold, which is what there should be. We go on the gold, there's the gold, but there's no sulfur. You will see that in almost any computer program that generates maps for you, even when they do background corrections. So my message here is if you're doing mapping, make sure you understand what that program is doing. And don't just trust a map. Okay? Look at the raw data. Look at the spectra itself. Okay. We're not going to talk about radiation damage, although maybe we will this afternoon. The microscopist's bane is radiation damage and what it does to materials. And there's our polymer guy. And sorry, that was a slide I put in just for you. You and I should talk a little bit later. Okay, I'm going to change gears now. And I'm going to shift to a different topic. Save, file, open. Again, something called the short version, which is really long. How long is it? This is my short version of eels. It's 100 and something slides. We also will not go through it. I want to let's plan on talking for say another hour, and then it's a good time to think about taking a break or stopping. All right. We're going to change gears to another spectroscopy now. This is another inelastic scattering spectroscopy. Okay, it's complementary to EDS. Okay, called electron loss spectroscopy. And what do we do? I'm going to talk about the same sort of series of things that I did for EDS. A little bit about the instrumentation, a little bit about the system, a little bit about data analysis, and then we won't get to advanced topics, I'm sure not in an hour's time. Okay, so what is electron energy loss spectroscopy? We measure the change in the inelastic scattering distribution of an electron beam going through a thin sample. Notice those words again, thin. It's going to be important to define what thin is. We defined what a thin film is for EDS already. Chi-rho T less than 0.1. That's a thin film. That's our definition. We're going to have a similar definition for EELS. what's a thin film for eels. Okay? Every time the electron beam interacts with the sample, there is a change in the characteristic energy and angular distribution, okay? The other important thing to remember, and you're told this all the time, and I tell people a lot, energy loss is a primary interaction event. You don't get an X-ray unless you've got energy loss. You don't get an Auger unless you've got energy loss. You don't get inelastic scattering unless you've got energy loss, okay? So it should have the maximum amount of information per inelastic scattering event. It does, but can we measure that? We can't always measure it. It is true that it's got the maximum amount of information, but can we always get that information? Okay, you saw this slide before. What I'm going to remind you is that when the beam comes in, two things can happen. It can miss everything and just go straight through, or it can interact with either the nucleus or the core. When it goes straight through, we get a beam called the zero loss peak. That is something that has either interacted with the nucleus, so the energy loss is near zero because that's massive and that's small, so we don't have much of an effect on it, or missed everything. Or we've lost energy, so we've knocked out an inner core, okay? So the zero loss peak is the characteristic peak that we see all the time. We usually call that zero loss. We say it's the elastic peak. Following that elastic peak, this primary electron can interact with the electrons in the solid. So what we see are interactions with the electron gas. We'll talk those in a minute. Those are called generally plasmons. And then we have a continuously decreasing background superimposed upon which are abrupt edges. Those edges, that onset of that edge, corresponds to the energy necessary to knock that inner shell electron out. So at this point, we're looking at 111 volts in pure beryllium. That's the energy it needs to knock out the K shell of beryllium, okay? You notice it goes up and then starts decreasing in energy. That's a general energy loss spectrum. They all look something like that, okay? The other thing that happens a lot is the electrons can interact not with the inner shell electrons, but the valence electrons out here, okay? That's a much weaker process because they're loosely bound. So we get processes down in the low energy loss regime, usually between a few millivolts up to maybe 30, 40 electron volts, okay? Those are generally called, in the nomenclature we use, plasmons. They're not all plasmons, but let's just call them that, okay? Those plasmon losses vary in energy as a function of atomic number, okay? You notice it generally goes from a few eV up to maybe 30-ish, okay? Once we get beyond that, they're no longer considered plasmons, okay? They're very characteristic, okay? The energies are reasonably well known, okay? And they're related to the density of the outer shell electrons. Okay, what do edges look like? Okay, now we're going to stop for a moment. I want you to think about this. Generally, when we do energy loss, most people restrict themselves to energy losses within a certain range. Why is that? Well, practically it's how your spectrometer is built. They're generally built to handle between 0 and maybe 2 keV, sometimes a little bit more. There are a few spectrometers that will go even higher. Okay, so if we're going between 0 and 3 keV, I'm just giving you a range, we can look at atomic numbers. Now notice this one, 1 to 11. Remember before I told you EDS, we can't do hydrogen and helium. In principle, you can do hydrogen and helium in eels. So in there, we're looking at K shells. K shells sort of look something like this if I was going to draw it. It's a sharp edge and a tail that drops off. Go a little bit higher in atomic number, 12 to 17. We can still see K shells, but we begin to see the L shells. The L shells are interesting, and we'll get to them in a minute, but they both have bright peaks, and also sometimes the peaks are missing. That has to do with the density of states that we're exciting. Go even higher in Z, in the 20 to higher range. We generally don't get K shells because they're above 3 keV. You'll get the L's and M's. Now we're starting to get very complex edges. Even higher M's, N's, O's, P's. The edges get very odd looking. There's nothing, well, I call them odd looking because they look nice and simple like a K. Okay, that's a schematic drawing of what they look like. This is real edges now. Walking through the periodic table. Let's concentrate on the lowering. K edges first. What do? They come up and then they drop down. All of them, you sort of see that. Now, notice the structure on those edges. That has to do with the electronic structure of the solid. Jump from K's to L's. L's are the transition metals now. Okay? Again, you see sometimes sharp lines and come down. These sharp lines are generally called white lines. Okay? You notice that the white lines disappear at a certain point. They disappear when the D band of the solid gets filled. Okay? And that's because the L shell is a P to D and a P to S transition. This is the P to S. The white lines are the P to D. And by the way, they're called white lines because the first time they looked at edges, they did it on a piece of film, and they printed the film, and they had a nice white line there, and that's why they got the name white line. Anyway, if we go up further in atomic number, so these are Ks. You see the K shells proceed all the way up in atomic number. Okay. Rarely do you look upwards up here. Most of the time, you're usually from aluminum down. Okay. We go even higher in atomic number, and we start seeing the M shells. Okay. Same sort of event. We get white lines on the M shells. Here, the white lines are a little higher. It's not the. This is the M45. That's the M23. Okay. Notice that when we hit a full D band at silver, those white lines disappear. The same phenomenon that's happening here at copper happens up here at sulfur. All right. So edges have complex shapes. Okay. I told you we can see hydrogen and helium. Here's an example of hydrogen and eels. All right. I want you to look very closely now. Any chemists in the audience? What's the core energy for hydrogen? 13.6 eV. There's your hydrogen peak. Okay. What are we looking at? An antenna mountain. Why? Because in addition to actually being in this energy range, there is a K edge there. This is hydrogen and metal hydride. If we had just pure hydrogen gas, we'd see the edge like we saw before. Pure hydrogen gas to me is boring. Okay? If I want to look at a hydride, I want to look at a hydride and a metal for energy storage or something like that. Okay? The problem with hydrogen and metals is that hydrogen peak edge, not a peak, edge, is bound up in the area that we have a plasma on. And how did I know that it's hydrogen, by the way? Well, I took the sample, I heated it up. And we can see the change in lattice parameter. There it is. And we can see that the edge disappears when I heat it up. Okay? Same thing for helium. Here's helium right there at just above 22 volts. Okay? There is an edge there, but it gets very difficult to see because it's also in the same energy range, 0 to 40 eV, where there's a lot of other structures. So can you see them? Yes. Are they difficult to see? Yes. In special cases, can we do the work? Yes. But I caution you to, if somebody says, oh, I want you to do energy loss of hydrogen in my metal hydride, it's going to be a difficult proposition. It can be done, and if we get time, we'll talk about it. All right. What's the other important thing to know about energy loss? This is important. In the X-ray case, all we did was we put a beam on the sample and we measured the X-rays. We didn't do much else. In energy loss, you have to do more. Because in energy loss, it's an extremely inelastic, extremely complex process and involves, if you remember this curve that I showed you before, oh, I can't use the pointer, I gotta use my finger. I told you before that if we have an atom in a solid and the electrons interact with it, they scatter. They scatter as a function of angle. This scattering process also happens in the inelastic scattering process. Okay? In the inelastic scattering process, what we have to look at is the inelastic angular distribution of electrons. And that inelastic angular distribution of electrons is very similar in that it has an angular distribution. Okay? If it has an angular distribution, if the energy losses have an angular distribution, we have to make sure that the angle that we use to collect electron loss signal is appropriate so we see it. Okay? That characteristic scattering angle for any energy loss event goes roughly as the energy loss that you want divided by twice the energy of the beam. That characteristic angle is important. If your angle is too small that you're collecting into your electron spectrometer, you will have no signal. If your angle is too big, you'll have plenty of signal, but you may end up getting something else. So how big is this angle? It should be the next slide. Oops. There it is. This is the characteristic scattering angle, that formula, as a function of energy loss for different accelerating voltages. Okay? And what I want you to look at is the numbers here. Okay? We're looking at numbers. Typically, you've got a microscope that's running in a few hundred kilovolt range. That typical scattering angle is a few milliradians. Okay? So if you have a very small aperture in the microscope of maybe half a milliradian or less, you won't get any signal. If you have a very large scattering angle, you'll get all of the signal. Okay? Let's see an example of that. Same sample. This is all carbon. All it made the same measurement for the same amount of time, same beam current. All I've done is change the angle that I'm collecting the energy loss spectrum from. First, a very small angle, 1/10 of a milliradian, almost no signal. Increase it to about 0.35, plenty of signal. And increase it to 0.5, lots of signal. Okay? What's the characteristic scattering angle? That guy for under these conditions, and I've forgotten what voltage this was done at, so I apologize. This was probably 200 kV, was 1 milliradian. Okay? So we could, if we can get even more signal if we're up around 1 milliradian. I was down at half. All right. You say, oh, okay, I'll just always put it on 1 milliradian aperture. Well, let's take a different material. Let's take boron nitride. Okay? Now you've got two edges, each of which has a characteristic scattering angle, and they're different. Okay? So when I go up to near 0.35, I got a lot of signal for the boron, but not very little for the nitrogen. What you want to do is when you have a multi-element species, make sure you have a scattering angle big enough to look at the highest energy edge that you want to look at. Okay? So calculate this number for the edges that you want to do, and make sure that when you set up your experiment and do the measurement that your scattering angle is right. Now, Nestor, you didn't tell me how I got the scattering angle. I forgot to do that. I'm going to back up a few slides now. Oops, I went forward. Where is my diffraction pattern? There we go. The scattering angle is the amount of the diffraction pattern that actually enters your spectrometer. Now here it depends on how you set up your spectrometer and whose spectrometer you have. Normally, in most systems, you will operate with the diffraction pattern sitting on the fluorescent screen. The kind of diffraction pattern that we look at, we blow it up really large so we can see the pattern. It's not the, it is the real scattering angle that has to get down into the spectrometer. You may blow it up very large. What I would suggest is blow up your diffraction pattern very large, put in your aperture to define the angle that you want, and now make your diffraction pattern very small so it actually goes into the spectrometer. Okay? If you left your diffraction pattern very large and just lifted up the screen, what's going to happen? The scattering angle, this may be what's going into your spectrometer, not that. Okay? So we'll do an example of that later if we go down to the lab and look at things. Okay? So make sure you know what the scattering angle is, and make sure that data actually gets into the spectrometer. Okay, I'm going to move forward now. There are a whole series of electron spectrometers. All the electron spectrometers work on the principle of Lorentz force. We talked about that for lenses. A spectrometer is a lens. It's a lens with a huge chromatic aberration. And we're taking advantage of that chromatic aberration to do spectroscopy. Now, so here's your spectrometer. It's a lens. Okay? Electrons of one energy are focused somewhere. Electrons of a different energy are bent, and they focus somewhere else. There are a whole series of different electron spectrometers. I'll give you examples of a few of them. Most of them, you will never see these. You will generally see this kind of spectrometer. It's called a magnetic sector. So it is a large area of a magnet with a coil around it. The electron beam comes in, it enters an area of uniform electromagnetic field, and it bends to a radius. Once it gets out of the spectrometer, it goes in a straight line. So electrons of one energy are bent one place, electrons of a different energy, lower energy, get bent higher, and they get scattered somewhere else. Somewhere downfield, we have either a slit or a detector that measures the energy loss spectrum. It happened to be one of the spectrometers I built a few years ago. Okay? Nowadays, what happens is you can actually go out and buy them. When we started doing this, we had to build our own. Okay? So the electrons come out, hit there. Here you see an energy loss spectrum. The reason you can see this is because I built my own lenses to go at the end of the spectrometer and blow it up to do things. How do these spectrometers work? The electrons come through, they go through some lenses, they hit a detector. The detector then measures that intensity distribution. Forget about that. Where's the next slide? Okay, sorry, I'm going to back up. I'm going the wrong way. Yeah, we get an intensity distribution, and then we measure the electron distribution at this plane. Okay? There's a lot of different kinds of detectors. I keep going the wrong way, sorry. There's the old photodiode arrays, which measure things in parallel. There's CCD arrays now. Basically, what you get is on your detector is a distribution of electrons, and your detector reads that out and transfers it to a computer. Again, we can talk a lot about this, but for now, we're going to skip that. There are two kinds of spectrometers. There's a pure spectrometer and something called an imaging filter. Okay, they are all nowadays the commercial ones are basically magnetic sectors. Although JEOL has one that's an in-column spectrometer called the beam filter. We're not going to talk about that one because you're getting a Gatan spectrometer, right? Okay. So you're going to get this kind of system. The difference between a pure spectrometer and imaging filter is not a lot. It's just a matter of how the lenses are adjusted. In one case, what we're doing is getting an image all the way through onto a detector. The other case, we change the post-specimen lenses so only the spectrum appears. What can you do with an imaging filter relative to a spectrometer? An imaging filter allows us to get an image through the spectrometer and allows us to either look at the unfiltered image, the elastic image, or an inelastic image. Now, will that help us for things like dislocations? This is why I'm showing this image. If I look at either an unfiltered, an elastic, or even the first or second plasmon losses, do I see much help in any of that? The answer is no. Why? Because the major contrast mechanism that's giving rise to this contrast is elastic scattering. So the inelastic scattering doesn't do anything. There is inelastic scattering in that image, but does it help us do an analysis of defect? The answer is no. Okay? How about diffraction? Will energy filtering help us in diffraction? The answer is yes. Where does it help us there? It gets rid of the background around the diffraction spots. Okay? Because it's a much cleaner background, makes it easier to look at the fine structure or the intensity in the inter-Bragg spacing regions. Okay. Makes it easier to do thickness measurements. Here's a unfiltered and a filtered image. And remember, we talked a little bit about, both I did and Hamish did, about how we can analyze the fringes to do thickness measurement by looking at the oscillations in the fringes. In this case, it's a lot easier because it's cleaner. This one, there's so much noise due to the inelastic scattering, we can't see it. The important thing about using a spectrometer versus a filter is the fact that we can get an image of something, we can stop the probe, and at a point get a spectrum, and that spectrum then tells us what elements are present in the sample, and that's what we're going to talk about next. Just like in the EDS experiment, you have to determine what the goal of your experiment is. Do you just want to detect something? Do you want to quantify it? Do you want to do some filtering and measure spatial distribution? Let's define the experiment very carefully. Okay? For the rest of this morning, we're just going to talk about these two. We may get to this very briefly just as an example. But I think I'm going to lose my voice again if I talk too much longer. We'll go for a bit, see how far we get. Okay, let's talk about data processing. I showed you an example, several examples of energy loss spectra. Here's a typical example one. We've got an intensity of the elastic peak, sometimes called the zero loss peak, the plasmon losses, then the background and the edges on top. If I wanted to do quantitative analysis, what am I interested in? What I'm interested in is the intensity of the element that's present. And the intensity of that edge is sitting on top of some kind of background. Now, in EDS, it was pretty easy. We said, well, there's a nice peak, and we drew a straight line between either side of the peak, and we got the intensity of the X-ray line. Here we don't have lines, we have edges. And the intensity of that edge carries on to infinity. So does the background underneath it. And it's nonlinear. Okay? So what we tend to do is we say we have an edge, we have a background, we fit a model to the pre-edge background and extrapolate that under the edge. We then subtract the extrapolated background from the total signal and say that's our net intensity. Now, the problem is that this background continues in infinity, and we've done a measurement and an approximation, and we've extrapolated that. The problem is this is a polynomial fit, and that fit will at some point in time actually cross over, because it's just a model. Generally, what we do is we say the background looks like an equation of the form intensity equals some amplitude, energy loss to a power. Now, if that was true, that'd be great. The problem is this value of power varies depending on the energy we look at. For very low energy processes, R is about 2. When we start getting up to very high processes, it goes upwards of 7. So this works, but it's phenomenological. I can make some hand-waving arguments and say, oh, it should be like this. But in reality, it's a phenomenological model. So it works. We can fit a background. We can extrapolate it. Okay? But we can't extrapolate it to infinity. The other important thing is if we have two edges, okay, the background for this edge is the background from this edge plus the tail from the edge before. So if we're going to do an analysis of a multi-edge system, what do we have to do? We do a background fit for one edge, we extrapolate it, then when we do this edge, we have to do a new background fit and include the tail of the edge before it, okay? One thing you never want to do is do a fit, subtract it, and then do another fit and subtract it. You will get an error, okay? So do a fit, extrapolate for a certain range, measure your intensity, and then do a similar thing for the next edge. I told you already that the background models don't work well, okay? Here's an example. I'm looking for boron in this. First of all, it's a really small amount of boron. I should have done this one in color. So this was there's a carbon edge, bit right here at 188, and I apologize, this graph didn't come out too well. There's a boron peak. Well, the question is there boron there? Well, it depends on how I did my extrapolation. If I did a fit here and I extrapolated down, if I did a fit here and I extrapolated, I actually went above the edge. So doing fitting is very difficult, especially when you have very small peaks. Sorry, this slide should have been first. Very small peaks on a huge background. Now, if I do subtract the background out of this, you notice that that's carbon and that is chrome. It's a chrome carbide. Okay, when I do subtract that background just to show it, there's actually a substantial amount of carbon there. The problem is you've got what looks to be a little peak on a huge background. All right. I'll get back to that example in a few minutes. All right. Can we quantify energy loss? I showed you a nice simple equation for quantifying EDS. Can we do the same thing for energy loss? The answer is yes, but we have to take a couple of different steps. If I wanted to quantify this spectrum, what am I interested in? I'm interested in the number of atoms that cause that peak. Okay? Well, the intensity of that edge is simply equal to the probability of creating that edge times the incident beam current. Okay? What's the probability of creating that edge? That probability is just the ionization cross-section times the number of atoms. So if I take that and put it in there, rearrange it a little bit, I can say the intensity of an edge, IK, divided by the cross-section, divided by the incident beam current, is equal to the number of atoms. Voila, quantification. Same problem that we had with EDS when we do absolute quantification. What do I need? I need a cross-section. I need the absolute intensity. Let's do the same trick that I did for for EDS for energy loss. Instead of looking at the absolute intensity, let's look at ratios. Take that same equation. Let's look at the ratio of element A to the ratio of element B. Those intensity ratios, if I go back to the previous equation, that guy, is going to be equal to some constant times the composition ratio. Same equation I had for energy loss. Composition ratio is the intensity ratio times a constant. Okay? That's how the easiest way of doing composition analysis and energy loss. You measure an integral over A, integral over B, take that intensity ratio, multiply by a correction factor, and you get the composition ratio. Okay? What's different is this, the correction factor. In EDS, it's more complicated. Remember, in the EDS, we had the ionization cross-section, but then we had the fluorescence yield, the radiative partition function, lots of other terms. Here, those terms don't come in. However, this is the total ionization cross-section. I'm going to skip this slide for a moment. Okay? Let me go forward. All right, so how do I get that ionization cross-section? We run into the same problem that we had with EDS. We, first of all, have to know what the ionization cross-section is. So we go to models to get it, or we do an experimental measurement. If we had a standard, put our standard in, measure the intensity ratio, measure the composition ratio, we have that constant. Store it, just like we did for EDS. What happens when I don't have a standard? Well, we resort to calculations. We do calculations of the shape and intensity of an edge. The problem is all of the models for ionization cross-sections are based on isolated atoms sitting in free space. In the real world, we don't have that. We have atoms bound in a solid. And all of the models tend to assume something that all atoms look hydrogenic. That is, they come in, there's a sharp edge, and it drops down. I already showed you on some of those experimental K-shell edges we get, there's a lot of fine structure. That fine structure is due to bonding effects. So right now, quantification is using simple models. The models are based on the work by Ray Edgerton, who's written computer programs to model every element in the periodic table as either hydrogenic model or an L-shell hydrogenic model. Okay? Do they actually match the real world? The answer is no. Okay? All edges have oscillatory structure, which is electronic structure, which is bonding material. Now, how do we get away with doing quantification? We get away with doing quantification by not trying to do very small windows, but do very large windows. So we wash out the effects of the bonding structure. We do an integration over a large window, that error gets smaller. Okay? It's not bad for K shells, it gets worse for L shells. I'm going to skip that. All right, and here's just an example, the K shells again. Remember, they come up and they come down like a hydrogenic model. None of those actually match that. But as long as we integrate over a relatively large energy window, that simple approximation of a hydrogenic sawtooth edge works. That's how all of the computer programs in all of the commercial vendors work. They assume a hydrogenic model, they assume Ray Edgerton's ionization cross-section, okay, to do the computation of the cross-section, and they put that, oops, back up. They put that, I'm going the wrong way, sorry. Where is, yeah, they put those cross-sections into here. Now, the other important thing is, and I skipped this slide before, the simple equation that I gave you, the intensity ratio is some constant times the intensity ratio works, and that's the model they use. But one thing I didn't tell you, that K factor, which is the ratio of the cross sections, varies as a function of the width of the energy peak that you measure and also the scattering angle that you did. Remember, I told you you have to choose the right scattering angle in order to get the signal in. That's because the ionization cross-section changes as a function of scattering angle. So in order to do quantification for eels, you have to do more than just measure the intensity ratio. You actually have to measure the energy window that you're using, and you have to know the collection solid angle, the angle of the electrons that are actually going into the spectrometer that you're measuring. You need both of those. You don't need the beam current, okay, but you do need those numbers. So that's where it's more complicated to do quantification. Now, the nice thing about the integrated eel systems that you buy today is they can read the parameters of the microscope. They can read the camera length, they know what size apertures you have, and they will know what the scattering angle that's going into the microscope for you and feed that into the computer program, okay? They will also make recommendations for the integration window. Back up. They will make recommendations for the integration window. Thing you want to avoid when doing quantification for eels is very small integration windows. You want integration windows large enough to smooth out any of these solid state effect oscillations. So you never want a 1 or 2 EV window. That's terrible. It looks interesting, you say do it, but these solid state effects are not easy to calculate. You really want relatively large windows, 20, 50 EV, or even higher sometimes. Okay, let's move forward. Skip. All right, practical example. This is a carbide and steel. It's a titanium nitride precipitate surrounded by an M23C6 precipitate in a piece of steel. Can we analyze this? Now, let's go forward for a moment. If we're going to do an analysis, what I'm going to tell you what you're going to want to do is you're going to want to do both EDS and EELS. Why is that? Well, first of all, here's an energy loss spectrum from that region, okay? We can see the iron, we can see the chrome, we can see the carbon. Nestor, you just told me all I had to do is fit the background and do an extrapolation and integrate the edges and get the relative intensity ratios. From that, with the cross sections, I can do the quantification. However, the metallurgists here will know that M23C6 is not just chrome carbon, it's not just or iron. There's a lot of other materials in it. Very specifically, in this particular M23C6, there's molybdenum. Now, do we see molybdenum here? How do I know there's molybdenum there? I know there's molybdenum there because if I go forward, in my EDS, I pick up the molybdenum peak. Where is the molybdenum in this spectrum? Okay, I don't see a nice big molybdenum peak. That's because in energy loss for high Z materials, we're not looking at molybdenum K edges, which are 6 miles that way. We're not looking at the Moly L, which is way the heck over there. We're looking at the Moly M shell. The Moly M shell It's a very broad, humpback whale type peak. And as Murphy's Law has it, that Moly M shell is directly underneath the carbon K. Okay? So how do I analyze Moly in eels in this situation? The only way to do that is to do some sort of deconvolution. So what I've done, or what I do, is I take some pure Moly. I measure the Moly M shell. I then measure my Moly carbide. Okay? This is even a simple one. Here's the M23C6, here's the Moly carbide. If I extrapolate the background under there, I can see where the Moly is, right? See just the beginning part of the Moly, which is that broad shoulder under there. I will take that spectrum, overlay it with this, scale it, fit it, subtract it out. Now I can get the carbon, and then I can get the rest of the material. So this was a, and you can see that here in the M23C6, but this is very old data, so I didn't have a lot of statistics. Nowadays, I wouldn't show you these kind of things before, but this is real data, and more than likely you'll have real things like that. Can you do that for everything? Well, look at Lave's phase. Lave's phase has a huge amount of Moly in it. That's very difficult to analyze. Okay? The question is, do I really need to do quantitative analysis in eels? Ask yourself which method is better. Is EDS better or is eels better? What are we trying to do? If all I wanted to do, let me go forward now, is show that this guy was a titanium nitride, I can do that very easily in eels. Why? Because, oh, where's the spectrum? Hold on. Oh, I'm sorry, the spectrum's missing. Apologize. This is the spectrum from the M23C6. I don't have the spectrum from titanium nitride, but there's the nitrogen K. Yeah, nitrogen K, titanium L. The well separated, I can easily show that that's titanium nitride. My point was, just when you start getting high Z's in there, you have to worry about things. And here the Moly was overlapping. And here's the chromium map and the iron map. They come up pretty lousy, right? That's because there's a lot of noise in here. Would have been much better to do that via EDS. In fact, if we do that via EDS, there we go. There's now carbon, nitrogen, titanium, chrome, iron, nickel, and Moly. Okay, combine them all. The Moly was done by EDS, the titanium and nitrogen by eels, and the transition metals by EDS. All right, let's spend about another half an hour and then call it quits because I'm getting.
Take a break now?
No, let's spend half an hour and then we'll stop. All right, we talked a lot about thickness effects. Okay, I talked a lot about thickness effects in EDS. I told you about the absorption correction. What about thickness effects in eels? Okay, and the problem that we're going to run into in eels and thickness effects is a phenomenon called multiple scattering. Okay, what happens is in eels you have a primary electron comes in, creates a core loss, and in the process of creating core loss can undergo other multiple scattering events. So what we'll have is core losses, super upon which is pleural scattering. Okay? How do we know how thick our sample is, or have we got multiple scattering? We actually have it in the energy loss spectrum. We have the zero loss peak, and then we have the inelastic scattering. You can show, and we can derive an equation that says that the ratio of the integrated intensity of the entire spectrum divided by the intensity of the elastic peak, the log ratio of that is equal to the thickness of the sample divided by the mean free path for inelastic scattering. That's a nice number to have. So in your energy loss spectrum, you measure this, divide it by that, and you get a number called T over lambda. T over lambda is an important parameter that you should know for your sample because it ultimately is going to define what a thick and thin sample are. Can we calculate lambda? Yes. There's an equation for it. That equation is phenomenological. It's based on experimental measurements. Okay. And there's an equation for it, and the references for it are down here. What happens to an energy loss spectrum as we increase our sample thickness? Okay. I've gotten rid of the slide I shouldn't have. This is the same sample for 3 different thicknesses. Actually, 3 different thicknesses. What I've done is for a T over lambda of 0.23, 0.6, and 1.2. What happens is when your sample thickness increases, all your intensity increases. Okay? In order to put this all on the same graph, what I've done is I've normalized these 3 spectra to a background at this point. What do you see in this curve? We see that as the thickness increases, the peak or the edge to background ratio gets worse. Okay? That's universal in energy loss. The higher the thickness, everything's increasing, but the background is increasing faster than the edge. Okay? What does this tell you? I want a thin value, a small value of T over lambda. So T over lambda is your controlling value, much like in EDS I talked about chi-rho T being less than 0.1. Here we're talking about what's T over lambda. And you want T over lambda to be very small. You want it to be well less than 1. If you're always around 0.2, that's a good number. Okay? I can't make my sample any thinner. What can I do? Well, lambda varies with accelerating voltage. Here's the same data again, but at 3 accelerating voltages. Again, the highest accelerating voltage has the best edge to background ratio. What happens to a ratio of edges? So now here's my, let's see now, what is this sample? This is nickel oxide, oxygen, nickel, okay? At 3 different thicknesses. You see what's happening. The background is increasing, as I go thicker and thicker, go from T over lambda of 0.4 to 0.7 to 1.4. Everything is increasing. Background is increasing faster than the edges. Okay? So what we want to do is how do we correct this for thickness effects? Well, there is a methodology. And what we do is we say we have an edge that's due to a low loss spectrum that has an inelastic scattering and then a core edge scattering, and then on top of that is inelastic scattering again. So this spectrum is due to a core edge convoluted with a low loss. So we do the inverse. We take the core loss, we Fourier transform this, we take the Fourier transform of the low loss, so there's the core loss, we take the Fourier transform of this, and Fourier transform of this, divide the 2 by each other, and deconvolute out the multiple scattering. So that's a thin film of graphite. So can we phenomenologically get rid of multiple scattering? Yes. Does it work perfectly? No. It's always better. So here I've done it for you. Is this nickel oxide again? Yeah, nickel oxide again. Thick sample of nickel oxide. I've subtracted off the background. You can see the multiple scattering. I do a Fourier transform of the low loss, Fourier transform of these, deconvolute it out, and there's the 2 core loss signals. That looks very pretty. Can we quantify this? We're going to do that here. I'm going to quantify the intensity ratio as a function of T over lambda again. Okay? If there is no thickness effect, the intensity ratio, remember that equation I gave you, says, where's our rater? Intensity ratio is equal to a constant times the composition ratio. There's no thickness dependence. So it should be a straight line. It should be a flat line. As soon as it goes off from a flat line, then we know we've hit the limit of that approximation. Where does that happen? Log T over lambda of around 1. So if T over lambda is greater than 1, can we do quantification? Not simply. Keep T over lambda less than 1. Keep T over lambda less than 0.5. So that's your measure of sample thickness and energy loss, T over lambda. I'm going to skip this. Let's end up, spend the last few minutes talking about mapping in a material, okay? I tend to be a spectroscopist, so I tend to look at spectra all the time. A lot of people would like to look at maps to see elemental distributions. Can we use energy loss spectroscopy to do elemental mapping like we did with EDS? The answer is yes, but it's a couple more steps involved. Okay. What are we going to want to do? We have an energy loss spectrum. Here's an energy loss spectrum. Okay. If I did a line profile through this, I can get a zero loss peak, a decreasing background, and then edges superimposed. Okay. If I want to do an energy loss image, what am I going to do? I'm essentially going to put an aperture, a slit around here, and I'll get an image. So here's the elastic peak. I'm just going to take that intensity, form an image. I can take a plasmon loss peak, these guys, and form an image. Okay? This happens to be boron nitride on holy carbon. I would like to know where's the boron. Okay? So what am I going to do? There's the boron edge. I'm going to get an image of that. Okay? So, oops, sorry, back up. But if I get an image of this, I'm going to get the edge plus the background that's underneath it. So the way to do energy loss mapping is to take an image of the core edge and an image of the area just before it and subtract this from this to get the net signal. Okay? It's going to be an approximation, but we can do that. So here's my boron nitrogen. I'm going to put an aperture around here and get the signal from here, which is the edge plus the background. It's that. Then I'm going to put an aperture around here and just get the background. Subtract this from this, and there's my net boron signal. Okay? Now, are there fancier ways of doing this? Yes. If you're getting a Gatan system, right? Gatan system has an elemental mapping setup. What they do is they say, what edge do you want to measure? Defines a window at the edge, defines two background regions before, takes an image here, takes an image here, takes an image here, so makes an extrapolation, subtracts the extrapolation background, and gives you the net window here. Notice a couple of things they always do. They never go right at the beginning of the edge. Why is that? Because of all the oscillations. They have a relatively wide window further back. They also take at least two windows before in order to get a reasonable extrapolation. The other thing is they also don't have very wide windows. Okay, they move it off the edge, but they're also not very wide. So this happens to be an example from silicon. Okay. You can produce some very nice maps. This is an example from Gerald in Germany. He's done that methodology. So there's the aluminum signal, titanium, the oxygen, and he's colorized it and put it all together. Does a very nice job. But it's all a color overlay. Here's another one from Richard Liepman of Biological Materials, where he's looking at the nitrogen, phosphorus, and sulfur signal in a biological system. And yet a third one in cell biology. Let's skip that one. Now, is there a problem with this? I'm going to pick a polymer example for my friend whose name I've forgotten, so I apologize. Okay, I did polymer is carbon. This is polystyrene and PMMA. Okay, so polystyrene is just carbon and hydrogen. PMMA is carbon, oxygen, and hydrogen. So I want to take my images. I'm going to do the two background images before. So there's background area 1, background area 2, post edge area 3. I'm going to process this, so this plus this, extrapolate the background under that, subtract it away, and there's my map of the oxygen. So I can say that this area is the PMMA, and this area here is the polystyrene. All right, now let's map the carbon. All right, we're going to map the carbon, and that looks awful ugly. Why does it look awful ugly? Well, first of all, this is the same area. I've taken a beam-sensitive material, PMMA, irradiated it for a very long time to get these maps. So I've done the background before and the carbon after, and then did the differences. Do I have something there? Yes, But this is the same area as this one. And you can see, look at that and compare it to that. Okay? What have we done? We've damaged the sample. Why have we damaged the sample? In order to get these maps, first of all, I've got to acquire spectrum for a long period of time. Not milliseconds, but seconds, sometimes even minutes. And I have to do it 3 times for every element, for every edge. Okay? So I've got essentially this area exposed, not for one map, but I have to do it 6 times to get 2 maps. 3 times for each map. Okay? And here's the before, and here's the after. Am I going to trust this elemental map? The answer is no. Right? I've destroyed the sample. All of the PMMA is gone. The only thing that's left is the polystyrene. Now, can we mitigate this? Yes, we can do better detectors, which they exist now. We can do cooling the sample to reduce radiation and radiolysis. So all that will help. You have to learn for your sample, can you do this? I showed you boron nitride first. Boron nitride's easy. It doesn't damage, at least not under the conditions I used. PMMA polymers will. So you have to ask yourself, what is the material I'm analyzing? When does it damage? Under what conditions? And understand that first before you try to do a measurement. So take your sample, beat the hell out of it, okay? Put it under high beam conditions. What's the right voltage? What's the right beam current? What's the right temperature before you do a measurement? And I don't care whether you're doing EDS or EELS. You should do it for both. All right, let's see. Let's go a little bit forward. I'm going to skip this. There's a lot of other information in EELS. Okay, I alluded to the fact that edges have a lot of structure on it. This is all carbon. That's amorphous carbon, that's graphite, that's diamond. Okay, all of this near edge structure is related to the bonding in the solid. So can you get some interesting things? Yes. Depends on what you want to look at. Amorphous carbon doesn't look too different. Graphite can look extremely different depending on how you took your data. Hang on, I want to go forward. Oh, so can you do near-edge structure analysis of allotropes of carbon, for example? The answer is yes, but you have to be careful that you don't destroy it. Remember, I said we were going to mention something about hydrogen. I'm going to rapidly skip through a few examples here. I showed you that hydrogen edges exist in EELS, but we really couldn't measure them because there's too much there. However, if hydrogen forms a hydride, okay, that's a little bit different. If it forms a hydride, then the hydrogen changes the plasmon structure because it changes the plasmon energy, which is related to the valence density of states of the solid. So we can look at the difference between magnesium hydride, titanium hydride, zirconium hydride. We can see shifts. So can you see hydrogen in a material if it's bonded? The answer is yes. Okay, but not everything. Unfortunately, that shift, notice, it's really big shift for low Z. As the atomic number starts increasing, that shift gets smaller and smaller. So you really need high energy resolution to see it. Okay, I'm going to skip this slide. Skip this one. Different forms of carbon. That was one I threw in for you in the end. We can look at different forms, different bonding forms of carbon that near-edge structure changes, so we can look at different allotropes of carbon, different types of polymers. Okay, but again, you have to be very careful when we're doing these things because these undergo radiation damage, and you'll destroy that very quickly. You can look at different oxidation states. This is copper metal. There's Cu2O, CuO, and YbCO. Okay, so we're looking at the copper edge. In copper metal, the D band is completely full. There's no white lines. In copper oxide, we started to move the D band, so we're starting to get the white lines. In CuO, the D band is fully empty, so we got nice white lines. We can now compare that with YBCO. Look at the ratio of the L2 to L3, L3 to L2, and compare that with copper oxide. So the copper in YBCO is copper oxide-like rather than Cu2O-like or copper metal-like. Okay? We just look at it. We don't have to, we can measure it. I'm skip this one bit. We can look at magnetism. Is anybody here interested in magnetism? Probably not. I'm going to skip magnetism. I'm going to get toward the very end. Plasmon resonances, I don't think anybody here is doing that, no. That's physicist in me. Move forward. All right, this is where I want to really end up. Let's do, we talked about EDS, we talked about eels. What should I do? My answer to is you should do both, okay? The salesmen for eels will say eels will solve every problem. The EDS people will say EDS will solve every problem. The answer to that is that's not true. You need both to do it. Let's do a direct comparison of EDS and eels. Comparison number one. This is 1980s. This is the 2000s. One of the big advantages of eels over EDS is its energy resolution. This is the exact same sample measured simultaneously in EDS and eels. We've got the oxygen K edge in eels, the oxygen K peak in EDS, the nickel L peaks in EDS, the nickel L edge in eels. Now, several things to notice. Notice the edges are a little bit this way from the peaks. That's true because the energies of the edges are higher than the energy of the peaks. Notice the energy resolution is significantly different between eels and EDS, okay? So if we had something else in here, would it be hard to see? The answer is yes. The example I gave you before was titanium nitride. The nitrogen K and the titanium K overlap completely in EDS. It's very hard to see it, but in eels you'll have the nitrogen K and the titanium L, you'll be able to resolve them very easily. Okay? The question becomes, which is better when your sample starts getting thicker? I've already told you there are thickness effects in EDS, and I've told you there are thickness effects in eels. So can we quantitatively compare the two? We have a measure of thickness now. It's chi-rho T, less than 0.1 for EDS, and it's T over lambda for eels. Okay? So the nice thing you'll have here, and I have it in my labs, is you'll have both EDS and eels. Okay? So we're going to take a standard test sample. Sorry, I need some water. Take a standard test sample. Nickel oxide, right? Nickel oxide. I can measure the zero loss. I can measure the plasmon scattering. I can get T over lambda. Okay? So I'm going to do a series of measurements. I'm going to do a simultaneous measurement as a function of thickness of an X-ray spectrum and an energy loss spectrum at the same time. Okay? So step number one, go to a nice thin sample. We're going to have, let's see now, do I have that? What's the thickness of this one? This is a nice, I'll tell you it's a nice thin sample. Just looking at this, probably T over lambda is about 0.2, roughly. I'm integrating on the fly. Yeah, about 0.2. All right, beautiful energy loss spectrum. And in fact, if we look at the number of counts, probably can't see it there. Here we're talking about 10 to the 5th, 10 to the 6th counts in that spectrum. Beautiful spectrum. The two were taken for the same amount of time. Now we're talking 10 to the 100,000 counts here. We're talking about 1,000 counts here. So, but that's a nice spectrum. Can I tell there's oxygen and nickel in eels? Yes. Can I say there's oxygen and nickel in EDS? Yes. Nice peaks, well separated, not much of a background. Nice peaks, well separated, starting to get substantial background. Okay. Now, what I want to do is increase the thickness of the sample. All right, so I want you to look at just this panel for a moment, because this is nickel oxide. I'll go to the other panels in a moment. Here's nickel oxide for two different thicknesses. The blue is at 0.2, previous spectrum, and the red is 1.75. So do I have in EDS, can I see the nickel K, the nickel L, and the oxygen K? Yes. How about eels? Can I see the nickel K for thin? Yes. Can I see it for the thick guy? It's almost gone. All right. What's happening? It's our multiple scattering effect. So I can do it in nickel oxide, I can do it in spinel, I can do it in a piece of steel, I can do it in boring nitride. As the thickness increases, T over lambda, the multiple scattering is increasing the background, and the background in EDS increases linearly with thickness. The background in eels is nonlinear. Okay? So what we're getting is the fact that for very thick samples, EDS is easier to see the signal than in eels. Let's see if this, yeah, here's a better example. This is a Joule microscope, 200 kV. Nickel oxide again, sorry. Okay, T over lambda 1.4, T over lambda 0.2. Beautiful edge here, we're losing it here. EDS, in both cases, I have no problem seeing it. The difference between, this is the raw data, this data is normalized. So I normalize to the background here, and I normalize to the background here. The peak to background ratio hasn't changed in EDS, substantially changed in eels. Okay? So, although eels has more signal, it has lots of near edge structure. It's really great to do physics experiments. If the sample gets too thick, eels fails. And it's not that the process fails, it's still there, all the information is there, it's just the background's increasing faster than the signal. So very thick samples, what's your methodology to go for? Try to go for EDS. Very thin samples, eels will always win. So thin samples, eels, thick samples, EDS. In the real world, you need them both. Okay, so this is a good point to stop. First, a little bit of water. Okay. Both for EDS and for eels, I want you to do a couple of things before you do an experiment. Think about the experiment you want to do. Think about your sample. How thick is your sample? I showed you both for, if all you want to do is qualitative analysis, can you use EDS or eels to do something? The answer is yes. If you want to do semi-quantitative analysis or quantitative analysis, then you have to start being careful. You have to know your sample. You have to know the conditions of the instrument. You have to know how thick your sample is. If your sample's too thick, I don't care which analytical technique you use, it'll fail. A nice thin sample, well prepared, with no artifacts, can you get great results in EDS and eels? Yes. If your sample's too thin, will it hurt EDS or eels? The answer is no. Will it hurt if you're doing dislocation analysis? Yes. What's the problem you're trying to answer? Okay? Hamish was telling you yesterday about how relaxation and surface effects will cause dislocations to pop up and go away. Are you doing a dislocation analysis? Well, then you have to have the right sample, the right thickness, and make sure you understand things. And do, in some cases, the dynamical calculations. In EDS and eels, can you do qualitative analysis of every sample? Yes. I can tell you what's there. I can tell you what elements are present. Do I want to quantify it? Can I do that? Yes. Do I need a standard? It depends on the material and the question you're asking. If all you're interested in is the relative ratio of element A to element B, and they're next door neighbors in the periodic table, it's easy to do. If as the elemental separation or the atomic number separation decreases, we have to begin more and more careful, both for EDS and for eels. Both EDS and eels have thickness effects. Can we mitigate those? Yes, in both cases make the sample thinner. But in both cases, as you make the sample thinner, we have to watch for other artifacts. Are you modifying the sample? Are you damaging the sample? If we're doing a polymer, do we have to worry about radiation damage? One of the things we were going to talk about this morning, when we were all done, was radiation damage. Well, realistically, we're not going to get to that today. Maybe we'll do that again some other time. So think about all of that. We talked a lot about understanding the instrument. If you don't understand your instrument, you won't be able to do a proper experiment. So I spent a lot of time talking about instrumentation. If I don't understand the instrument, I can't understand how I detect something. If I can't detect it, then I can't measure it. Okay? And if I can't measure it properly, I can't quantify it. So know the instrument, know your detectors, know the measurement, know how to do your quantification. Those are the right steps to do things. Does it take a lot of work? Yeah.
I thought you just pressed the button.
And Hamish always just pressed the button. Quant. Don't trust the button that says quant unless you have verified it. Okay? Verified the methodology. Verify the computer program that came with your microscope or your quantitative analysis system. Put in a standard that you know, and that's not always easy to do. How are you going to get the standard? Okay? Put it in, test the quantification. Does it work? Never trust a map at low concentrations of an element. High concentration, sure, no problem. When something's at 50%, 90%, yeah, it's easy to see. I want to look at 1% levels. Am I going to do a map to test? No, I'm going to look at the individual spectra. Don't trust an AI system to go out and analyze your analysis. It'll tell you everything's there. Remember to tell the computer what's really there, okay, and check it. Okay, I really specifically pulled out that map example to show you how somebody can make a really huge error. And when something's not there, but the computer said it was there, it's because he didn't do the right experiment and didn't look closely at the data. Okay? Data is king. But before the data, you need the sample. So spend your time making a good sample, do a careful experiment, look at the data. Can you quantify things? Yes. It's going to take you work. Okay? Nothing's free. Okay? All right. I'm tired of talking. I got to stop for a bit. All right. Cheers, guys.